We would now like to felicitate our eminent lecturer, Professor Jose Wudka. So I request Professor TV Bharat to do the honor, please. We would now like to now I will request Dr. Subhaditya Bhattacharya to share his thoughts about this program. You can come in here.
Professor Jose Wudka, Professor TV Bharat, Professor Bosant Borua, my colleagues and dear friends, welcome you all to IIT Guwahati. It's a great pleasure to see such a nice gathering, and I'm sure that all of you are going to enjoy this course. I will say a couple of words about our program. We have the leading expert on effective field theory, Professor Jose Wudka, all the way coming from UC Riverside. He is going to give a set of 10 lectures to build the subject basis. Then we have 5 lectures by me, essentially to fill some of the details. And apart, we will have guest lectures by some of the very eminent particle physicists coming from all over the India. Professor Joydeep Chakraborty from IIT Kanpur, Professor Sanjoy Bishwas from RKMVU Kolkata. Professor Satyonarayan Mukhopadhyay will join today, and he is coming from IACS. Professor Shankho Banerjee from IMSC, they will all come. And Professor Soumitra Nandri from our department will also talk about various aspects of effective field theory. So together we have very intense program, and I'm sure this will give you different flavors of effective field theory, which is now at the forefront of the particle physics research. And we will share the lecture notes on daily basis via email. And you are welcome to discuss with anyone about any physics issues within and beyond the lecture schedule. And we all expect that you will make the most of it. Regarding logistics, we have made some necessary arrangements for your stay, for your food, etc. In case something is missing, you are most welcome to talk to us or two of the research scholars who are working very hard, Ovik and Niloy. And the miscellaneous file that we have shared with you carries most of the informations, but anyway, if there is something missing, please let us know. And also you can see the weather is very good. You are very welcome to take tour of the campus and also in the city or nearby places, but without bunking the lectures. Okay, so with that, I welcome you all and thank you very much.
Thank you, sir, for your welcome note and sharing us with the schedule. Now I would like to request Professor Bosantoranjan Borua to share a few words about our department.
So first of all, I would like to welcome Professor Jose and thank you for his time to be here to train our young students. Then Professor Bharat for facilitating everything, especially the participants to be here and my colleagues. So it is a pleasure to say a few words maybe about the department. So Department of Physics was established in the 90s, and it started with PhD and MSc programs. Now it is also having PhD, MSc. Now it is having a BTech program. So we have a 4-year BTech program in engineering physics, 2-year MSc program, and we have PhD program. We have about more than 200 research scholars pursuing research in number of areas, for example, condensed matter physics, both experiment and theory, laser and photonics, high energy physics, gravitation and cosmology, quantum optics. We have MSc students per batch, it is around 60. And similarly, we have BTech students, 4-year BTech students, again about 60 students. So we have a number of outreach programs also. There is an outreach department in the institute. Either it is through the outreach department or directly from the department. We have activities either in the institute, or we also go outside to popularize science or physics in particular. In case you come across someone who is interested in studying physics at IIT Guwahati, then there are a number of ways they can come in. In BTech engineering physics, the way is through the JEE exam or advanced JEE exam. For MSc, one has to first qualify the BSc exam, and then after that there is a entrance test called JAM. After that they can join the MSc program. And then for PhD, there are 2 routes. If you want to join with fellowship, then you have to qualify GATE, and then there will be interview followed by written test followed by interview, or sometime interview alone, or it can be through CSI or JRF. So there will be number of ways that someone can come to study physics in the department. Now, coming to this particular course, I'll be interested to know from which places you are coming. So I assume you are coming from various places. So other than IIT, can you please ask you to raise hand who are coming from outside IIT Guwahati, just to have a look. Okay. So I would assume more of you are from outside. So, so how far from, say, around Delhi, anybody, or south, or which side? Who is think that he is from the farthest? Okay, very difficult to tell because so anybody from northeast? Okay. So what I would like to tell Professor Jose is that I have found over the years that in northeast topics like high energy physics and cosmology are very popular. In fact, I sometimes wonder that if I will be able to attract to my area these many students. So I think the number is less, but there will be many more. And then many brilliant students are especially interested to this particular area, theoretical physics, cosmology, high energy physics. So one piece of suggestion to the students. Again, I don't have a clear idea. Are you people already in PhD or you are in, say, completed MSc? Most of you, Subhaditya?
Most of them are research scholars.
There. So you have already chosen the area. Okay. So now you know the topic. It is standard model, effective field theory. My piece of suggestion will be like, eventually we are trying to understand the nature through different route. So this is one route. So while studying, you will have definitely an interested area, but keep your mind open, because you know that science in general or physics in particular, they are entirely connected. If I consider standard model, the famous experiment, which is the Large Hadron Collider, where you collide maybe 2 protons, how you accelerate the protons, what is the principle? Lorentz force, right? So Lorentz force is in your electromagnetics, Griffith. So then there is a need of vacuum, so how to create a vacuum, how to, why the magnetic field is needed in this particular case, how a giant magnetic field is created. So all these things are interconnected. So when you are a scientist, okay, you may have a particular line, you may be confined to analysis, or you may be confined to the design, you may be confined to data collection. So eventually your specialization can be different, but if you keep your mind open, have a broader outlook, that will be always beneficial for your growth only. Then other example will be, of course, not exactly related, but people probably never thought that a Michelson interferometer that you often see in the BSc lab, and then probably you got bored seeing the Michelson interferometer so many times, and people would not have thought that this Michelson interferometer eventually lead to the detection of gravitational wave. So, so the summary is that keep your mind open. Eventually you have to grow as a physicist. You will have a specialization, but at the same time, you also see that you have a broader outlook. With these few words, I hope you will have a great time. I hope there will be a lot of interactions with Professor Wudka. It is a great opportunity for all of you, and make the best use of it, and all the best. Thank you.
Thank you, Dr. Borua, for his wise words. Now I would like to request Professor Bharat to share a few words about the CET and the Gyan course.
Thank you. Thank you. Professor Borua, Professor Subhaditya, and other colleagues from physics, I join with you all to welcome Professor Wudka from University of California, Riverside, to IIT Guwahati, and also we humbly welcome all the participants coming from outside different parts of India, and welcome you all to CET and IIT Guwahati. This is a very interesting and auspicious occasion to start the Gyan program, and second Gyan program from phase 4 under CET. And we just concluded one course last week, and this is the second one we're starting today. And Gyan is a very interesting concept and program which is initiated by Ministry of Education, Government of India, for leveraging the international experts, global experts, to engage themselves in the advancement and enhancement of scientific knowledge of India, and also at the same time to provide the global experts to immerse themselves in the Indian science and technology, and also start collaborations with Indian professors, and also start engaging the Indian students. From CET, Center for Educational Technology, we have conducted several of such Gyan courses in the last phases. In this Gyan 4, we have submitted 20 proposals from different departments from IIT Guwahati, and so far 12 got approved, and this is the second one, and 5 more we will get the approval very soon. And this is a highly competitive, and the meticulous planning what Professor Subhaditya told, that actually speaks a lot about how this is meticulously organized and why this was successful, why this has been selected. Very interesting aspect is that from the Gyan course, there's a recording that is taking place, and many participants are also there online, apart from the participants who are here. And Professor Subhaditya actually shortlisted, right? So many registrants actually showed interest on this particular topic, and he shortlisted for physical attendance, and others are participating in online mode. So interesting aspect is this recording eventually perhaps turns into a content that is available for general public, something like a NPTEL MOOC we've been organizing, right? So from IIT Guwahati itself, faculty members from across the IIT Guwahati from different departments have contributed in developing 700 courses, which are all up on YouTube for free of cost, anybody to view. And eventually this might also turn into one of the NPTEL courses. So that provision is still there. And also this will be enabling for students to get additional credits for physically attending and then giving exam. So this is one of the advantages. And also CET has organized several TechWeb programs, Coursera MOOC programs, and many other programs, initiatives are going parallelly. Also, there are training programs for the defense forces. So we have so far conducted 3 training programs, and many other programs are going to happen. So these are some of the initiatives from CET, Center for Educational Technology, and this is very interesting moment because this land is known for observational astronomy, and this particular place itself, Prague Joshidapura, has a name astronomy, and Professor Wudka comes from Department of Physics Astronomy. So this is a coincidence or whatever it is. So I'm sure this will be a resounding success, and from CET we provide all the support to complete this particular course and then fulfill all the requirements from the GYAN. Thank you so much.
Thank you, Professor Bharat, for his words. Finally, I will request Professor Wudka to share a few words.
Thank you. Thank you. This will not be a long speech. So I just wanted to thank enormously the department and the IITG for the opportunity to come meet you all and to tell you a little about the research that I've been doing. I also wanted to encourage every one of the younger people to talk to one another. After all, I'm not going to be your colleague. Your colleague is sitting next to you. And so this is a great opportunity for you to interact with one another and learn from one another. You are the future of the field, and that's one of the beauties of this type of events that brings young people from all over the country to interact, meet each other, and hopefully start collaborations, or at least a way of talking to one another. If I can facilitate that, let me know. I'll be more than happy to do it. So I know tea is waiting. I'm between you and the tea, so I don't want to interpose. And so let me just thank again the institution, my colleagues, and all of you for coming. What I hope will be a rewarding experience for all of us. Thank you.
Thank you, Professor Wudka, for his words. It's actually an absolute honor to have him with us. So we are looking forward to learn a lot of things from you, sir. So with this, we will conclude this inaugural ceremony. We extend our heartfelt gratitude to all the dignitaries for their valuable presence here. Thank you again, everyone, and once again, welcome to this course. I hope we are going to have a very productive and engaging week ahead, as Professor Wudka mentioned. So now we will have a short tea break, and after that we'll commence with the lecture series. So wish you a very happy learning. Thank you.
And then
press for 3 seconds.
Okay, so let's see if it works. Okay, that works.
You can wear.
Like it?
Yes.
Okay. Can they hear me or not too much?
Not too much.
Okay. Maybe that's good. Is this a good place?
Yes. Yes. Sir.
Okay. Can
Yes.
is it work?
Yes.
Does it work?
Yes. Yes. Sir.
At the back, can you guys hear me? They told me to wait until 10:30, so I'm waiting until 10:30. It's 10:25. What's that? Oh, so I have to be over there? Have to, from here on? Okay. So you want to hide, I go over there. Okay. Okay. Then I need to move this. It's okay. Okay. Everything's ready. 3 minutes. No, not for me.
I think it will better illuminate if we close this.
I don't think so. Maybe. Yeah, I think so.
Not yet.
1 minute. All right. Welcome to this one, the first lecture. I'd like to thank you again for coming. Before I begin, let me just point out that I hope to lead this in a rather informal way. If there are any questions, please raise your hand. I'll try to answer your questions as we go, as much as I can. Okay. In the introduction, I beg your patience. I'm going to go through an analogy or allegory that try to justify or represent more the type of physics that I'm going to talk about and motivate it. So with that, let me begin. Okay. 66 million years ago, there was a huge volcanic explosion that lasted for a very long time on the west part of India. It spewed out about 1 million cubic kilometers of basalt and formed what is now the Deccan Plateau. At the same time, coincidentally, there was a huge asteroid impact in the Yucatan Peninsula. Both events produced an enormous amount of disturbance in the planet. It spewed out a lot of carbon dioxide. The weather changed. Enormous amount of soot and debris went off into the atmosphere. And as a result, the dominant species died. As you can see from this clever illustration here on the left, they're all dead. But not everything died. Small furry animals that evolved into mammals survived. And these animals thrived. Not all the dinosaurs died, however. The smaller ones did survive, evolved, and became birds, like this chicken here. So what does it have to do with high energy physics? Well, about 16 years ago, a new collider fell on us in Geneva. It's called the LHC. And it coincided with a slew of very high precision and sophisticated low energy experiments. And as a result of the data that came from it, many of the existing models, the dominant species in high energy physics, died because the data killed them. And what I want to talk to you about is of the small furry high energy theory animals that have survived this cataclysmic event in high energy physics, and argue that they have a very good chance of thriving in the future. What I will not talk about is the equivalent of the high energy theory chickens in this course. So for that, you'll have to go to some other place. Okay? All right. So let me start with that. Of course, the small furry animals is the high energy theory version of effective theories, and that's what I'm going to talk about. But the reason they've become increasingly popular is precisely because the data has been so effective in disposing of the leading models that we relied on for such a long time. So let me start with a very basic idea of the effective field theory. EFT will stand throughout this course by effective field theory. I will not write it out, it's long, but I will use the acronym continuously. All right. Let me start with an explanation of what this is supposed to do. For this, if you assume that the standard model is a very good description of physics as we know it, then and you realize that we have not seen any new physics so far, then the EFT is a mechanism for classifying, understanding all possible new physics, and P stands for new physics effects that generate deviations from the standard model. It's as simple as that. The one thing that I've just told you that's important is that the new physics is not directly observed. So these are all virtual effects that we'll be talking about for the next 10 lectures and the 5 discussions and the 5 conferences. And so the EFT, again, is a way of studying and understanding this situation, this type of situation, in a systematic and consistent way. So how do we do this? And what I'm going to do first is to tell you what I'm going to call the recipe for constructing the effective field theory. That is, for constructing the tool that we will use to understand all these deviations from the standard model. And the recipe has, as you see, 3 steps. The first step requires you to choose the light symmetries your theory will have. That is, what are the symmetries that you actually observe now? Within the standard model, we know that. That's the gauge symmetry, SU2 cross U1 cross SU3. That's a local symmetry, a gauge symmetry of the standard model. There are other symmetries that the standard model obeys, like lepton number and baryon number, but those are considered accidental. That is, they follow not from the internal structure of the standard model details, but from the fact that we have chosen a particular set of representations, set of particles within it. And so they're considered accidental. Nonetheless, you can choose, and again, that's you can choose, which symmetries you want to include except for the gauge symmetries. The gauge symmetries, you have no choice. I will talk about that later. The discrete symmetries, like lepton number conservation, the global symmetries, lepton number and baryon conservation, you have no choice. You have choice. The local symmetries, as I will argue later on, you have no choice. First step. Second step is you choose the light fields. Actually, nature chooses the light fields for you. You turn on the LHC, you see what comes out. For each particle you assign a field. Those are your light fields. Those are the ones you see. You're done. If you don't like to do LHC physics and you like to do QCD at low energies, you turn on your machine, you see your pions. That's it. Those are your light fields, period. So depending on the kind of system you're looking at, the experimental results give you this component. And then the last step is you write down all local operators, that is, operators composed of these light fields and their derivatives to a finite order that obey the light symmetries that you've chosen. There's an infinite number of such operators. I will call them generically O. And I hope you like the the effective Lagrangian, that is the tool you use to calculate all effects from the underlying theory and from your light field in the light field involving the light fields, is composed is written as a linear combination of these local operators with unknown coefficients. Yes, sir. What's it? I'll have to come closer. I can hear you. Yeah.
What are you calling as light?
What am I calling light?
Yes.
Okay. So the question is, what are the light fields? Right. Exactly. Yeah. So suppose you are doing an experiment at the LHC, and then you produce. What did I do?
You are fine.
Oh, you're going to get the, okay, yeah, okay. So you, in an experiment at the LHC, you turn it on, let's not do the LHC, let's do LEP. It's an older collider. And so you turn the experiment on, and what do you see? You see electrons, you see photons, you see muons, you see neutrinos, you see W's, you see Z's at the time, and you see taus. You know, you see the B quark, you see the C quark, you see all these things coming out. Those are your light fields that you choose because you're interested in describing the physics available to you at the time, which was the physics that can be probed by LEP. You turn on the LHC, you have a little bit more reach. You have the top quark and the Z and the Higgs. And then with all these things, those are all the fields that you can probe directly, because they show up in your experiment. But in principle, there could be a billion other fields that you cannot produce because you don't have the energy or the experiment is not right for that or whatever it is. those are not there in the light field collection, but you can still probe them through virtual effects. And the thing that I'm going to argue during the course is that this type of construction, these are made out of only light fields, this type of linear combination of light fields is the right way for studying all virtual effects of and all direct effects between your light fields and all virtual effects produced by any new physics that you don't observe directly. Okay. The number of terms in this sum is infinite. There's an infinite number of operators you can type. And the operators have arbitrarily high dimension. And so by dimensional analysis, these quantities CO have units of some sort. Not always, but in general, they have units. And so the higher the dimension of the operator O, the higher inverse dimension correspondingly the coefficient has. Okay, that's something to keep in mind. For those who have taken regular quantum field theory courses, at least the ones I took, the fact that the Lagrangian has terms of arbitrary light dimension seemed to imply a disaster. It was a theory that one should immediately dispose of, has no content whatever that one can extract. It's too vast, has too many terms in it to be of any use in describing nature. I'll talk about that in a minute. Okay. And another thing that we've been told, or I was told when I was a graduate student, is that if you have terms of higher dimension, higher than 4 dimensions, the theory is non-renormalizable, and therefore it's useless. That's not true, period. So even though we have terms of arbitrarily large dimension in the Lagrangian that I'll talk about is renormalizable. That's renormalization or renormalizability is not an issue in this theory. What is a problem is having an infinite number of coefficients. If you want to determine that infinite number of coefficients, you need an infinite number of measurements, and so you would think the theory has no predictive power. But that is not the case. And the reason for that is that the operators, in all interesting cases, can be classified into a series of finite groups that I labeled leading, subleading, sub-subleading, etc., in the sense that these generate the largest experimental effects. These create smaller effects. These create even smaller effects. And since all experiments have a finite sensitivity, there comes a point where the rest of the operators are irrelevant for the experimental situation we're facing. So we can drop them, keep just a finite number of them, and now you have a theory that is renormalizable. It has a finite number of coefficients, and you can work with it. Now, which hierarchy, how this hierarchy comes about, we'll see during the course. It depends on the type of physics that we're looking at. So we're looking at collider physics. There's one kind of hierarchy that's useful. If you're looking at low energy QCD, that's another hierarchy that's useful. We'll see the motivation for that in detail. But I'm just giving a quick overview of what's coming up. With that, let me move on to a specific example. And for that, I'm going to, it's very simple. And it's intended to be very simple, but it's still illustrative of what's coming up. In this universe that I'm asking you to imagine, there are 2 particles. There's a heavy electron, charged particle, and there's a photon. That's the whole universe. Okay. In this universe, the electron that I told you about is heavy. The photon is light. So with the language that I had used before, this simple Lagrangian, the photon, non-interacting photon, is the standard model. And the electron cannot be seen because I don't have enough energy, and I'm assuming that, to create electron-positron pairs in this universe. I just don't have enough money. The photons I can buy have energies that are below m/2, this big m/2. So I cannot make electrons. Nonetheless, I can still do experiments at low energy that involve virtual electrons and probe the physics underlying my standard model. Okay, now in this example, I already know, because I have this foreknowledge of what the underlying physics is. I will come to kind of the inverse situation a little bit. But at the moment, I know the new physics, the heavy physics, which is this, and I know the standard model, and I'm going to try to describe from the point of low energy the new physics virtual effects. That's known how to do. So if you're using functional integrals, what you do is and this is the jargon, you integrate out the electrons like this, and you get an object which depends on M, on E, and on A, the photon field, which I called S sub psi. And S sub psi is, from my point of view, the effective action. It contains all virtual effects produced by the electrons, everything. That's it. There are no electron lines in this world, external electron lines, precisely because I cannot make them. I don't have enough energy for that. That's my assumption. And I should say that's a realistic assumption. Since we have seen nothing beyond the standard model, we don't have enough energy, clearly, to produce anything that, or not yet, anything that underlies the standard model. So this is not a crazy example. It's a simplified version of our current reality. All right, explicitly. Well, this integral, this being a Grassmann integral, I can just do, or just formally do. You get this, that SI is the log of the determinant of this operator. Of course, one cannot evaluate this exactly for arbitrary photon field A, but one can do an expansion in inverse powers of m. Why is that useful? Because in this case, I'm telling you, the mass of the electron is heavy. It's heavy with respect to the energy I have available. So the more masses I have in the denominator, if I do an expansion of this form, if I do an expansion of this form, then the more suppressed the term, the contribution to S psi. If you had arbitrary large energy, that would make no sense. I can just make a lot of energy, right? I produce a lot of energy to the thing. This makes no useful sense. But in my case, this thing here, d slash, it's a derivative. It's like energy that I have available. M here is a large mass compared to this. That's my reality. So this object is small, right? And so this thing will go, like a slash to the n times something that gets increasingly suppressed by inverse powers of n. And therefore, its effects will be smaller and smaller and smaller. And since in this world, as well as in our world, the experiments are supposed to have finite sensitivity, there will come a value of little n where the effects coming from these guys are unobservable. They're in the noise of the experiment. So I do this, in graphic terms, the first term that has n equal to 2 looks like this. Then there's a term that has n equal to 4. There's no terms with odd terms. That's whatever his name is. Furries? No. What's his name? First term? the one that the trace of odd number of gamma matrices is 0. I forget this. Anyway, so if you do the calculation, you find that there are no terms with n, little n odd. There are all terms with little n even. And here you have the thing. And so now, what does this do? Okay, so physically, you have a term that has 2 photons, term that has 4 photons, and so on. This term is produced by the electrons. It affects the index of refraction of our photons in this world. So there's one way of measuring the effects of new physics without producing it directly. This term produces scattering of light by light in this world. And that's another way of trying to probe the new physics virtual effects without having the energy to produce them. We can measure the change in reality, in QCD. We can measure the change of the index of refraction by whatever particles go in there. Now, what it's much harder to do is to get a scattering of light by light. You need enormous intensities of lasers. And this is the reality we have now. And that's because the particles that in our world appear in here are relatively heavy. Okay, so again, let me recap. Each term, the one thing I did not mention, each term in the sum is a separately gauge invariant. It doesn't look like it, but it is. The useful expansion is for energies below m. If this becomes of order 1, then you have 1 minus 1. The denominator here is very small, and each term becomes relatively large. And this expansion is just not useful. And lastly, when you do these diagrams, you have to remember that the energy coming in here, in all the legs, is way below the mass of the particles circulating inside. So there's never a unitarity cut. You don't produce the heavy particles. And that's everything. I will come later on today to a case where actually you screw up. You violate this rule, and you'll see what happens when you do that kind of extrapolation. Okay. Oops. Oh, here we go. Okay. Now, let me, just for fun, evaluate the term that has 2 photons. I can actually do it. I can evaluate this term here when little n is equal to 2. I can just calculate it. And you get this thing here. Looks like this. I'm sorry, it looks like this. It has 2 photons, has a kernel inside, kind of a vacuum polarization term that I should have called it pi, sorry, but I called G. And it has these properties. This is Bose's symmetry, gauge invariance, and you can calculate it explicitly. It looks like this, and I've used dimensional regularization in doing this calculation, and you get this. You get a term that is independent of the external momentum, which is the Fourier transform of the quantity x, which is the difference of the 2 photon positions, right here, this thing, and it's divergent. And then you get a bunch of terms that look like this, that in the same spirit that I mentioned earlier, I'm going to expand in powers of 1 over m. And it looks like this rather uninspiring set of objects with funny coefficients. I would like to bring to your attention a couple of things about this. First, it's energy over mass, the expansion, which is the expansion parameter. By assumption, that's small. What does that mean? I'm assuming k is much smaller than m. So in that sense, k is small. That means x minus y is large. And I'm assuming the photons are relatively widely separated. Okay? I'm not looking at photons almost at the same time. To do that, I need a lot of energy, which I don't have. The other thing I'd like to point out is these factors of pi squared that show up. These show up because all the graphs that I'm looking at are one loop. And because of that fact, the the contributions are suppressed by this thing and by increasingly larger and significant and rapidly increasingly numerical factors. The divergent piece is calculable and it's not observable. It will be absorbed in the renormalization of the light theory. That's something you cannot measure. The rest of the terms you can, or could. So I put it all together and see, okay, so this is my effective Lagrangian, which I used to call S psi, and it has several terms. It goes like this, 1 plus 1. This alpha is E squared over 4 pi, as usual. E squared is the gauge coupling of the heavy particle. And as you see, it goes like alpha over numerical m squared, alpha over numerical m to the fourth, multiplying 2 photons with increasing number of derivatives or factors of the low energy available to us. There are corrections that have higher number of gauge couplings, and there are corrections that have higher number of inverse powers of m. The generic form of each coefficient is e to the 2n. That's because, as I mentioned, there's no odd number of photons. Divided by 16 pi squared. 16 pi squared comes from doing the loop integration. As you can see, this is more than 16 pi squared, right? They have, pardon me? F mu nu, yeah, thank you. I'll come back to that. I'll mention that, thank you. This is a little bit more than 16 pi squared, that's fine. But there's the fact that you get a pi squared there is, and multiplied by a large number comes from it being a loop. The reason we don't get A separately, we get the F mu nu, is gauge invariance. It's exactly gauge invariance. Okay. This is also, I'm ignoring, okay, I'll stop there, okay. So you can see this, all these terms are calculable. If you have enough strength, you can calculate e to the fourth. If you really have many graduate students, you can calculate e to the sixth, not beyond. But who cares? Because we won't have enough energy within our lifetimes, including your lifetime, to measure the e to the 8 terms. We just won't have it. So, why suffer? If you have a way of actually calculating all the terms, that's a different issue. Right? It's a fantastic power to you. But if you're going to go the brute force method of calculating Feynman graphs with increasing number of legs just for the fun of it, I suggest you take a hobby and do something else. I mean, this is not fun. It's not useful. Okay? One should keep in mind what is useful. All right, the expansion is, and again, the expansion is useful only for energy below m. Okay? Only below m. So this is what happens if we don't know, if we know exactly what the new physics is. But in fact, we don't. So what do we do then? Well, in that case, we follow the recipe I told you about. So what are my symmetries? My symmetries are Poincare invariance and U1 gauge invariance. So that's my symmetries. Ta-da. What are my light fields? A mu nu. That's it. Simple. But I have a U1 gauge field. And so in reality, a mu doesn't show by itself, but with an F mu nu. Right. And I'm here ignoring non-perturbative effects. I'm sorry. Okay. I could talk about that if you want, but separately. It just takes me too much off here. And then I'm supposed to build all local operators involved using this field, F mu nu, and that satisfies the local symmetries. Okay, because I used F mu nu, U1 is fixed. Everything will be U1 invariant. And so the only thing I have to do is ensure that my operators are now Lorentz invariant. And so, you write down all the F squared terms. Oh, they all look like this. You say, wait a minute, you forgot one. You can have an F tilde, you can have an epsilon tensor. It's not forbidden. But in fact, this happens to be a total derivative. for any value of n, and so it doesn't produce any observable effects, any perturbative observable effect. And you can go ahead and do the same thing for the f to the fourth, and they look like this. And in that case, you can have f tildes. You can have f tildes and so on. And it's a matter of patience and being careful to make sure that you don't miss any terms in this kind of expansion. But with a little bit of patience, you get them all. And as you see, you get terms that have 4 photons. And they describe light by light scatterings. And for those who some of you might know, this was calculated early on, and many years ago, by Euler and Heisenberg. This is not Euler the mathematician. It's a different Euler, okay? It's a modern Euler. And Heisenberg, for the case that I just mentioned. Here they calculated this loop graph with 4 photons, and they got the terms that involve this guy and this guy. They did not get f tilde terms. These terms violate CP, okay? But because the original theory is CP invariant. But in general, you can imagine that there's, I don't know, another fermion that's also heavy that couples with the gamma 5 to the photon, and then you will get these terms with an f tilde. So once you're living in this universe and you're given the problem of finding new physics beyond photons, then you look at this type of expansion and you devise experiments to measure C1, C2, C3, C4, sorry. This should be a 4. This is not the same as this, it's a mistake. Okay. And the observations. At least I know that by dimensional analysis, I must have a factor of some heavy scale in the bottom. It has to be, otherwise it makes no sense in any way. So the higher number of photon fields that you have and derivatives, the larger the number of inverse powers of this lambda that replaces the m that I had before, and it represents the scale of the physics that I'm probing. This is a physical number. It's not a cutoff. This is a physical quantity. This is the mass of the heavy guys, the scale, or the equivalent of the standard model Weber. It is a physical quantity. Okay, so I'm going to use lambda, and I know lambda is also often used for a cutoff, but throughout this, lambda is not a cutoff. There will be one case in the lectures where I use lambda for a cutoff, but then I'll put lambda in red, and I'll put cutoff underneath it so that it can be differentiated. Okay? And so this lambda is a physical quantity. And so if you measure all these objects here, and you find in your world that, in this world, that the C1 and, I don't know, C3 are not 0, then you're very happy because you know there's something beyond the photon physics that you can see at low energies. But on top of that, part of the tools that we'll gather along the way in this course will allow you to not precisely determine, but to estimate reliably lambda. And that is also very useful, because then you can go to your experimental colleagues and say, if you build a collider that has this energy, you will find new physics and you will get a Nobel Prize. And I want a piece of that. Okay? So that's why this is used. Phenomenologically, it's very useful to be able to estimate this lambda. It's also satisfying to be able to do a low energy experiment and infer something about physics that you cannot see directly. So I am going to repeat myself because this is really important. And so I beg your patience in doing this thing. The prescription: choose the light fields, choose the symmetries, construct all operators with the light fields that satisfy the symmetries, and the linear combination of those operators describe all the effects of that between these light fields and all virtual effects that can be generated by new physics beyond that effect, provided there's a mass gap. Yes? In the previous slide. Wait. Microphone's coming. Wait. I'm old and I don't hear very well. No, I'll come closer. There you go.
Yeah, at the bottom of the slide, it's mentioned CP violating new physics, not only a heavy vector like fermion. Could you explain this? That I mean, CP violating operators, how they can arise apart from
yes. Actually, technically, it's not very difficult. It's not very difficult. Instead of having this, so the question, everybody here, sorry. Imagine that instead of having this coupling here, EA slash, we have an A slash gamma 5. Okay, not even A slash, but instead of having just A slash, I have A slash multiplying 1 plus X plus C gamma 5. And then you have a coupling that has a 1, and then another coupling that has a gamma 5. And then when you do the graphs, here you have terms here that have one gamma matrix, one gamma matrix A, one gamma matrix, and one gamma 5. And then the trace of gamma, alpha, beta, gamma, delta 5 gives you an epsilon. Okay. This? This? This?
No, sir.
One more. This?
So this is a recent one that you talked about.
This?
Yes, sir.
Okay.
So if we expand this, if we expand this, so then it should come 1 by lambda squared and 1 by lambda to the power of. So I think the expansion is. So the power of the lambda is wrong, I think, and even the coefficient.
So here it's lambda to the fourth. There will be more terms that have lambda to the 6 here. Is that your question? No.
So the summation. The
Here, the summation.
Yes, sir. So if we expand this, then I think the power of the lambda should be 1 by lambda to the power 2, then 1 by lambda to the power. So, but here all are lambda to the power 4.
No. You see here, this has units of twice 2m, 2 mass, mass to the 2n, mass to the 2n, and then you have this has to have dimension 4, and you have ff dimension 4, and then I have lambda to the n, box to the n over lambda to the n that has no units.
So, and what about the coefficient? So Cn.
This Cn.
So one is C1, then C2, then again last one is again C2.
This have no units.
Last expression was he is talking that last term should be C4. Oh, that's, yeah. C4.
Oh yes. I made a mistake. This should be 1, 2, 3, 4, but I missed it. I'm sorry. I apologize. No, I apologize. Yeah, this is not the same as this. There's no reason for that to be the case. I mean, it could be, but it's not. I mean, it's just an error. An error. I apologize. Oh yes. Oh no.
If this heavy fermion have chiral coupling with the photon, let's say, why does it generate a CP violating f squared term?
Oh, it does.
Okay.
But as you see here, the question is that it's a total derivative.
Okay.
FF tilde is a total derivative, so it has no perturbative effects. Okay. Go on. Okay. Okay. Then remember. Okay. All right. In that case, all low energy virtual new physics effects, and I know I'm repeating myself, so I won't repeat myself all the time, just this time. Okay. Are described by this thing. The quantity NA is an index, it's an integer, and it's organized so that this product here, this quotient, OA over lambda to NA has dimension 4. Because that's, so that the CAs, again by definition, here are dimensionless. If the new physics is known, you can calculate the CAs. I showed you how to do that for the new physics. If the new physics is not known, then the CAs are not known, but they serve as a way of parametrizing all possible new physics effects. So at low energies, that means below the scale lambda, all possible new physics is parameterized by CA. If one person has a particular type of new physics, it will generate one particular set of CAs. Another person has a different kind of new physics, it will generate different kind of CAs. In optimal situations, if you have a perfect set of measurements that are very well made and they can differentiate, then in principle, they are able to differentiate between different sorts of new physics by measuring their virtual effects. Unfortunately, perfect situations rarely occur in our lives, but we'll do the best we can, and I'll show you how. This expression, as it is appropriate for what I call decoupling new physics. That is, all new physics effects go away when lambda goes to infinity. When the new physics doesn't disappear when some scale goes to infinity, that's another possibility. There's a different kind of expansion. I'll talk about that later. I thought this was good enough to give just an example to hold on to. But I want to emphasize this is not every type of effective theory. Lastly, two last things. For weakly coupled new physics, we will see that these couplings here are bound by things of order 1. What does this mean? It means it's not a 10 to the 4. It's not 10 to the 3. It's not 100, but could be 10. Okay? So it's not a precise statement, and that's the world we live in. But if somebody presents an object like this, and I'll talk about that in a minute, where CA is of order 10 to the 4, the calculations and the results obtained from them using that value of CA are wrong. Are just wrong. Should not do it. Okay? And lastly, and again, I know, the effective theory approach fails if we go at energies above lambda. If we could have energies above lambda, we don't care about EFT. We will all be looking at the new particles. Who cares about the virtual effects? You can see them in your in a detector or something. Yeah? Anyway. All right. So I want to, I think, finish today with talking about illustrating the limitations that I mentioned about the construction of the effective theory. So the first one I want to talk about is what if you decide to just break gauge invariance a little bit? And the answer is there is no such thing. You cannot break gauge invariance a little bit. You break it a little bit and it spreads. It's like the plague. It will go everywhere. You cannot tell the theory, I'll just break gauge invariance here a little bit and I forbid from radiative corrections to occur. You can break gauge invariance a little bit. You cannot forbid radiative corrections. And once radiative corrections turn on, then this little breaking will propagate, will generate all possible gauge variant terms, and your theory will stop being unitary. So don't break gauge invariance. Renormalizability is something that I say we will deal with. Having a non-unitary theory is really bad. don't have non-unitary theories. They're not good. Okay. So I will talk about this later on when I do more formal developments. But I'd like to illustrate here especially what happens if the effective theory is used at energies above lambda, and what happens if some of the coefficients are really very large. Okay? So first, here it is. I'm going to assume that I'm going to assume an effective theory, very simple. Very simple. The point is the illustration, not how interesting phenomenologically this is. And I'm going to purposefully violate this commandment that I put on myself that energy should always be below lambda. And so I'm going to imagine a universe where I have the standard model, and the new physics, the only thing it does, it creates a new interaction between electrons and neutrinos. That's it. And this is, I didn't write it down, but this is kind of a current interaction between an electron current, a neutrino current, and you put them together. It's a little bit like what you see at low energies generated, say, by the Z. The Z couples to electrons and to neutrinos, and you can imagine at energies below the Z, it looks like an electron current multiplied by a neutrino current. But this is a different Z prime. And in this universe, this is what the new physics does. It makes electrons talk to neutrinos. The standard model also allows electrons to talk to neutrinos to the real Z. And so you can calculate with this type of theory, I just told you, it's a standard model plus a current interaction that has some coefficient. That I told you, it's go C over lambda, in fact, in this case, lambda squared. And I can calculate at tree level the cross-section, E plus E minus to, say, going into muon neutrinos. That's what I'm. So this new physics makes electrons talk to muon neutrinos. It's artificial, I mean, it's contrived. It illustrates the point. And you calculate the thing, and the standard model has just one term, a Z exchange, and I have my beautiful interaction between the 4 fermion, the 2 electrons and the 2 neutrinos. You calculate the cross-section. You get one term that has 2 Z propagators, one term that has an interference, only one Z propagator, and one term that's produced by this guy alone. And they have coefficients A, B, and C that are this. SW is the weak mixing angle. G is the SU2. SW is the sine of the weak mixing angle. CW is the corresponding cosine. G is the SU2 coupling in the standard model. What else? Oh, and here's my C over lambda squared. This term comes in the interference term, so it's going to be linear in C over lambda squared. And there's a term that's, oops, yeah, sorry, term that's going to be pure, okay, the square of this, come from the square of this diagram, that goes like C squared over lambda to the 4th, and here it is. The factor of 8 pi, 4 pi, and so on, they don't come from a loop calculation. That's the phase space calculation for the total cross-section. This is the total cross-section. So this is not a loop diagram in any way. As you can see, they're tree-level diagrams, but it comes from phase space. And then you can plot it, and here's I'm plotting for lambda equal to 300. And you get a huge term from the Z resonance. Of course, formally it's infinite because I didn't put a Z width. I could have done that. You have a huge increase here at the Z. And then it drops. And then it starts increasing. And then it keeps on increasing. And it goes increasing forever. Large and large and large. And if you go back to your quantum field theory books, you know that the cross-section cannot increase indefinitely with energy and maintain unitarity of the theory. The theory becomes non-unitary. And it's not that this is not a unitary theory, it's that you push the theory to a place that it doesn't apply, it just doesn't work. what happens physically. If you increase the energy of the electrons, eventually you can probe the new physics that's generating this guy, say a new Z or something else, and you get a different behavior in the cross-section. But that's not coded into the effective theory that assumes you will never do that. You cannot do that. And so going beyond the E equal to lambda is forbidden. If you do, the world doesn't come to an end. You don't get an infinity. Nobody knocks at your door saying, you violated the law. What you find is an unphysical result. It's not that the theory is wrong, but that you're applying it wrong. The second illustration is what happens when you have very large coefficients. And for that, I'm going to use a different example. Okay? So I have the standard model, and what I decided to add is a new term that couples two W's to a photon and to a Z. Again, this is something like this. I know it doesn't look like a SU2 cross U1 cross SU3 invariant term. I can make it so. It just is clearer to present it this way. So like this, it looks like this, WWZ, or WW photon. And it has, you can count the number of the dimension. This has dimension 6. I need 2 units of mass in the denominator. And I put here not lambda squared, but mw squared. The reason is that in the 90s and 80s, that's what people did. They put mw squared. There's no problem. You can say, well, yeah, just write it like that. Then this little lambda has mw squared over big lambda square in it. That's okay. You want to do like that, that's fine. And I put a factor of V because if there's a photon, the photons usually couple universally with a gauge coupling. And so now I have this new term, and I can calculate its contribution to the vacuum polarization, and you get this. Now I faithfully noted that I cannot apply the theory beyond lambda, so I cut off the integral at the scale lambda, because I cannot go beyond that, and I get this object. I regularized a divergence using this thing as the cutoff. That's not quite the thing to do, but that's what people did. And again, I'm illustrating the problems you generate when you do this. Now, I have the vacuum polarization for the W. And the graphs are very simple. You have 2 W's, and you have 1 photon line or a Z line on top. It's a straightforward graph to evaluate. It looks like this. And Q is the momentum of the W. Here, M is the mass, and so I have the vacuum polarization. I can calculate the propagator, get the poles, and find the physical masses. And you find, well, this is here. The physical masses are the poles of the propagators. And you say, okay, let me ignore what I said before, that little lambda has a dependence of, it has a dependence on big lambda or something. Just ignore that. In this case, you can just put q squared minus mw squared plus this equal to 0 and try to find the solutions for q squared. And you find 2 solutions. One solution is q squared equal to s1, which is minus mw to the 4th over lambda squared, which is a tachyon. And then you have another one that is to q squared equal to s2 equal to lambda squared. And you say, oh, effective theory is really problematic. Because before I put in that term, I had a very nice W pole. Great. Plus corrections. And now I put this one term, and look, the W pole disappears. The only pole that makes physical sense is at energies that I cannot probe. It disappears. And then the other, suddenly, a tachyon also appears. It's a disaster. You put an effective theory, and your theory makes no sense. And the reason that happens is not that the effective theory is a disaster, but that you put in a coefficient that's huge. And I'm talking about 10 to the 4th, 10 to the 6th. And so the theory formally becomes strongly coupled if you have such a large coefficient. And the calculation that you did before, simple one-loop graph, is irrelevant, because the two-loop graph is more important than the one-loop graph. On the other hand, if you do what I told you before, and you say, okay, what this little lambda is, it has a factor of 1 over lambda squared, because that's the scale of new physics, and it comes, from the same argument as before. Everything is fixed. One pole is mw squared, and the other, which is appears, but it's unphysical in the sense that it lies outside the reach of the theory. It's a pole at order lambda squared where my theory is not reliable. So the whole thing makes physical sense. So if you put very large couplings, the theory makes no sense. If you put very large energies, the theory makes no sense. If you don't do that, you're good. So, 4 minutes to spare. Any questions? All right. With that, thank you for coming. And I'll see you, hopefully, in the afternoon. Thank you. 4 minutes. Yes.
Yeah.
Previous slide.
So you have this one loop contribution to the W map of finite. There is no divergence, right? So is it with the counter term, or is it coming out to finite?
Say again.
So I'm just saying, if this pi w is coming out to finite, is it in presence of additional counter term that you have to add there, or without that it is finite? That's what I'm asking.
No, it's not really finite. It's not really finite. Let me tell you what's done. Okay, let me tell you what's done and see if I can manage that. Okay. Exit. All right. So the graph that you calculate is this. So W. Is it visible?
Yeah.
Oh, it's visible. Okay, so this is a W, and there's another W, and then I put here this guy, say photon. This coupling, say, comes from this vertex. This is standard model.
Oh, sorry, I missed it. Sorry, I missed it. It's okay. Fine. It's
Okay.
regularized. Lambda is
And then this diagram that you see there is infinite. But so the problem with this approach is that you're double thinking, like in 1984. You're on the one hand, you're saying the theory doesn't apply above lambda, so I'm going to cut off the integral at lambda. On the other hand, you forget that it applies all the way to lambda, and you say, I'm going to assume that the coupling here is independent of the scale of new physics. And if you think like that, then you get tachyons, which is kind of cool but wrong. Okay. Other questions? We good?
Yeah, if you have more questions, you can ask. You can ask later also.
Oh, absolutely. There's no prohibition asking questions. I'm going to be around here until Friday, and later on you can reach me via email. Okay. All right.
Okay, so
can have tea.
let's conclude the first session then.
Yeah, thank you.
Let's thank Jose.
Okay. Thank you.
So we will meet for the next session. Is it immediate or it's immediate, right? Okay, okay. So, yeah.
Okay. You're on.
Okay. gravity is omitted, and some of the basic principles that we talk about is of course the method is quantum field theory, the principle of gauge invariance takes a key role, and etc. So, this is a slide which tells you a historical interlude, like how it started. Many people think that the starting of finding the fundamental constituents of the universe was essentially the discovery of electron by Thomson, followed by several other things which you all know, and just because of the time constraint I may not repeat that, you can look at the slides later. And standard model is essentially constituted of this many particles. We know that there are quarks and leptons, there are force carriers which are gauge bosons, and there is this piece which is called Higgs boson, which has been the most significant discovery of particle physics of late. Okay, all right. So, let us move on. And when we talk about the observables, most often we talk about cross sections and decay. And once again, this is something that we you all know, that when two particles collide and produce two other stuff, it can give you number of events, which in a more formal way we talk in terms of cross section, and this has essentially these pieces, the one part which is called the initial flux, how exactly the particles are colliding, how many of them, and etc. There is something called the phase space. For example, if your center of mass energy of a collision is very small and the particles that you are trying to produce are very heavy, then you cannot produce it. That is the basic idea of phase space. And then there is something which is inherent to the kind of process that you are looking into, and that is what is called the matrix element of the interaction. So, these are, and many a times instead of talking about the full cross section, you talk about differential cross sections, the differential distributions in terms of the produced angle or phase space and so on. And most of the particles, the heavy particles, so Jose was trying to classify that there are heavy particles and light particles, but within the standard model, excepting for the lightest electrons, say for example, all the heavier leptons are unstable, they decay into the lightest of its kind, and all the gauge bosons excepting for photon, they also decay. So, therefore, most of the particles are not stable, and the decay width can be computed by what is called the similar process, and the only thing that is not here that is not there in the decay width is the initial flux, because it is a particle which is sitting at rest and decays to two pieces, and this is how exactly you can calculate. And if it decays to many particles, then the total decay width is a sum of that, and the individual channels can be calculated via this what is called the branching ratios, and the total decay can be related to the lifetime via the inverse one. Okay, so let us get back to a basic of the construction of this standard model. Let us first talk a little bit about quantum electrodynamics, because that is a key thing. So, the principle of gauge invariance is very important here, like you know, we all know about the Dirac Lagrangian. So, this is psi bar I gamma mu del mu psi minus m psi bar psi. This is the what you call the free Dirac Lagrangian. Now, if you take a transformation on psi, which is like a global transformation like e to the power I q x psi x, then the bar of it will transform exactly like e to the power minus I q x, and in that case this slide is it is not behaving properly, I am sorry. So, the basic point is that you can I mean it is clearly in under global symmetry the Lagrangian is invariant, but when you do a local transformation like psi x going to psi prime x, which is e to the power I q chi psi x, and psi prime bar will be then this guy, but when you look into the derivative term, then the derivative will also act upon this parameter which is locally space time dependent, and so therefore, there will be an additional piece, and so that will not keep the Dirac Lagrangian invariant. So, therefore, there is a problem in actually addressing that thing, but this slide does not work. So, I am sorry, maybe we should go back to the PPT this PDF is not working correctly. I don't know. Yeah, okay. So, yeah, this is not working. I don't know the reader that this can we this one. Okay, let's see how it goes. Yeah, this is better. This is better. This works. Okay, I'm sorry. Is it going to come at all? No, it doesn't like QED, I guess. Okay, so yeah, so this is the point that this Lagrangian, the free Dirac Lagrangian, is not invariant under U1 local gauge transformation. So in order to keep the Lagrangian invariant under the gauge transformation, we need to bring forth some other fields. So that's what we would like to do. So so basically what one does that instead of this usual partial derivative, people introduce this covariant derivative, which is defined in terms of del mu minus IQ mu psi, where mu is what is called the gauge fields. Now, together with the fact that mu also transforms, it has a freedom so that it can go from mu to mu prime, which is equal to mu plus del mu chi. If we keep these two transformations together, then we can show that d mu psi prime will be exactly equal to e to the power I q chi d mu psi, and that will make the kinetic piece invariant. So, this derivative term of this local parameter, so that get cancelled, and d mu psi prime is exactly equal to e to the power I q chi d mu psi. And in a sense, we can say that the kinetic piece psi bar prime I gamma mu d mu psi prime, this is equal to psi bar I gamma mu d mu psi, so which is invariant. So, the Dirac Lagrangian remains invariant under local gauge transformation when we change this partial derivative to covariant derivative, introducing this piece gauge field in it. And in this process, what we do that once we write this Lagrangian in terms of the covariant derivative, we have the free Dirac Lagrangian plus this interaction term, which is essentially the interaction with the photon. So, this interaction with the photon is proportional to the charge q, which is the U1 charge, and one can find the equation of motion via Euler-Lagrange's equation, where now this equation turns like I gamma mu del mu psi minus m psi is equal to q gamma mu psi. And many of the credits are given to this gentleman, and I think you all know who is he. This is the name by which this what is called the Feynman rules for QED are constructed, and this is for initial state particle, final state particle, initial state antiparticle are called V bar, final state antiparticles are V. Similarly for photons, for propagators, for photon propagator, fermion propagator, and this is importantly the vertex that we talk about, which has a factor like minus I q e gamma mu. So, finally, this is the full QED Lagrangian, which is the Dirac part in it, plus the photon part, which is minus 1 by 4 f nu nu f nu nu. You remember Jose actually explicitly constructed an effective field theory, knowing that this is the light fields which perhaps constitutes the universe. Okay, so f mu nu is what is called the field strength tensor, and it is explicitly written in terms of del mu nu minus del nu mu, where mu and nu are the photon fields. And the way that we write it in terms of f mu nu is because this part of the Lagrangian is actually the also invariant under U1, where you remember mu goes to mu minus del mu chi. So there are, once you construct a beautiful theory, the taste of pudding lies in eating. Unless it is tested in experiments, it's not the theory of nature. So what did QED do? That QED actually paved the way for something called the observation of Lamb shift in hydrogen atom, and that Willis Lamb, he won the Nobel Prize for observing this, and this was calculated using QED. And this is very interesting, that the anomalous magnetic moment of electron was actually calculated very, very accurately. So the theory gives you a prediction like this, up to alpha to the power 5 order, where the experiment actually measures it very accurately. The accuracy is almost like 1 part in a billion, and this was one of the major things for which people started believing in QED to a great extent. So this was a success for this kind of a construction. And immediately once we sort of know this kind of QED, then we can calculate this kind of interaction like E plus E minus going to mu plus mu minus, and following the prescriptions and using the Feynman rules that we have for the QED. And you have the external legs, the vertex factors, the propagators, which constructs this matrix element. And as I told you that once you calculate the matrix element squares for the unpolarized beams, it has to be all the spins have to be summed over for initial and final states, whereas you also have to take the average of the initial state spins, and that is the factor of 1/4 sitting here. One second, it is gone. Okay, so for unpolarized beam, we must take an average of the initial state spins. That's what the point was, and then if you calculate it, it comes out as simple as e to the power 4 into 1 plus cos square theta, and you can then calculate the differential cross section, and this is also very simple, and this becomes alpha square by 4 is 1 plus cos square theta, where alpha is the famous QED constant in terms of E square by 4 pi. And if you plot the differential distribution in terms of cos theta, so this is usually symmetric because it is symmetric in terms of cos theta. This is e to the power 4 into 1 plus cos square theta. But what you experimentally observe is not exactly the same, but it's a little different one, and we will come back to this issue later. So this is what happens to electron-positron annihilation in QED, but we are exactly not matching with the experimental observation shown by these dotted lines. Okay, so this brings us to the next topic, which is the beta decay and weak interaction. You all know that beta decay was one of the radioactive decay processes which was actually observed long time ago, but the beta decay spectrum couldn't be understood unless we actually assume the presence of neutrinos. I will talk about that in my next lecture tomorrow. And it also tells us that this neutrino has to have a very tiny mass if we have to feed the beta decay spectrum. And importantly, what it also tells us that the effective coupling through which this process should occur from the half-life of the beta decay should be way lesser than this alpha that we actually constructed, which governs the electromagnetic interactions. So therefore, people sort of postulated that this must be a different interaction, and they sort of called it weak interaction. And there was then this very famous experiment which is called the Wu-Zambler experiment in 1957, which actually showed this cobalt to nuclear beta decay, and it shows parity violation. Now what was observed, that if parity is conserved, then the electrons which are coming out with respect to the initial spin direction should be the same. But it was seen that there is this preferred distribution to the initial state spins when they are aligned for the initial nuclei. and this showed the parity violation, and yeah, this is specifically the observation that the electrons which are emitted along in opposite direction of initial cobalt nucleus spin are actually different, and that gives rise to the conclusion that the weak interactions must violate parity. And this gives rise to the construction of what you call the SU2L cross U1Y gauge theory. And what is the basis of this construction? It basically says that the leptons and the quark contents of the universe, I mean, it should be arranged as a left-handed doublet and right-handed singlets. So, basically you have the left-handed doublets, which most often I call this small l, which is basically stands for the left-handed doublets, which constitutes of neutrino, neutrino and electron, the left-handed components in it, and the right-handed electron sits as a singlet, it is not a doublet. Similarly, for the quarks, that the left-handed quarks forms a doublet, which we often call capital Q, and the right-handed components sits as a singlet. So, the electroweak interaction is essentially embedded in this SU2L cross U1Y theory, where you basically have these doublets which transforms under SU2L. The right-handed components are singlet under SU2, but they have some appropriate hypercharges, which we will show how exactly they are. So, yeah, what is the left-handedness and right-handedness? I mean, they are basically the helicity eigenstates of the fermions. You can say that the right-handed particles are essentially those where the spin and the momentum are aligned. For the left-handed case, actually it is in the opposite direction. And formally, left-handedness is defined like half into 1 minus gamma 5 psi, which is often called this projection operator PL psi, and similarly for psi r, it is half into 1 plus gamma 5 psi, which is PR psi, and this follows the projection operator, and in gamma 5 in Dirac-Pauli representation is 0 I 0 with having those following properties. Once again, something happened. Okay, so yeah, why do we distinguish between left and right-handed cases? Just because, I mean, in weak interactions where parity is violated, they behave differently. So that's basically once again the answer. So now we construct this gauge theory, the electroweak interaction under SU2L cross U1Y. So what we have to do, let us remind ourselves that the for fermions, we have to, in order to respect the local gauge symmetry, we have to change the partial derivatives to covariant derivatives. So for lepton doublets, we have to write it like L bar I gamma mu d mu L L, and for right-handed singlets, it's E r bar I gamma mu d mu E E r. Now, why do we distinguish between these two different covariant derivatives? Because as we mentioned that the left-handed doublets transform under SU2, where the right-handed singlets do not transform under SU2. So, the d mu L is essentially del mu minus Ig, W mu A sigma A by 2, these are the SU2 generators and these are the SU2 gauge bosons, and this is the U1 Y field strength not tensor, I mean this is the U1 Y gauge field. This is what you call the hypercharge associated with the left-handed doublets. This is the strength of the U1 Y coupling, and d mu E r is del mu minus Ig prime, Y r b mu, where this is only the hypercharge which is contributing to this covariant derivative, because the right-handed electrons, they do not transform under SU2L. Okay, so once you have this construction, then you can expand this covariant derivatives and the interaction terms can be written in this particular way. So, you have the left-handed doublets interacting with this W mu A sigma A by 2, then you have the interaction of the left-handed doublets with B mu, the right-handed electrons only have interactions with B mu. Now, you have to basically do this calculation, I mean it is not very difficult, but once you expand those terms, what you actually obtain is that there is a charge current interactions between the electron and neutrinos with this what you call W mu plus minus, which is a combination of W mu 1 and W mu 2, and which gives you vortices of this particular way. And on the other hand, there are neutral current interaction with neutrinos like nu EL, gamma mu nu EL, which is you can also write it in terms of nu E fields in this particular way. And so this gives rise to the Feynman graphs in this particular way, and this Z is a linear combination of B and W mu 3. And basically there are two orthogonal combination. The combination which couples to the neutrinos is Z, and the other orthogonal combination is actually the photon. And obviously because neutrinos doesn't have electromagnetic charges, so they do not couple to photon. And in this process, this is the Weinberg angle, which is the ratio of G prime by G, tan theta W is equal to this, and YL is equal to minus half. So this YL that we introduced as the hypercharge for the left-handed doublets has to be equal to minus half, so that the neutrinos only couple to Z. And sin theta W and cos theta W, the sine and cos of the Weinberg angle has to be related to this strengths like G prime by square root of G square plus G prime square, and the cos of theta W is G by square root of G square plus G prime square. And now you do the same exercise, is to collect all the terms with the electrons. So the interactions with the electrons once again has a piece of W mu 3 with B mu and etc. So once you do collect all these terms, there is no surprise, but you get something which is expected, that you get the interaction with the photon. Okay? So, so when you collect the terms with electron, there is one term which is actually just the QE decoupling, the one that we actually started our discussion with, E bar gamma mu E A mu with E 0. Here there is an important choice that YER, the hypercharge of associated with this ER field is equal to minus 1. And there is another thing which is this E is equal to G prime cos theta W. So this is remarkable that in this SU2L cross E1Y construction, we could actually correctly embed the electromagnetic interactions. And similarly, you do the same exercise to couple all the terms with Z, and what you get is a term which is like this, that it has a vector part CV gamma mu and an axial vector part which is CA gamma mu gamma 5 term. And this CV and CA, these are actually related to this isospin and hypercharges. So the magic relation that embeds or that rather relates the electromagnetic charge with this isospin and hypercharge is this guy, that Q is equal to T3 plus Y. Now let's check how it actually does the case. You remember, for this left-handed doublet, we constructed this doublet with nu EL and EL, right? Now for this doublet, the T3 is actually plus half for the upper component and is equal to minus half for the lower component. And with YL equal to minus half, you can put it here. You can see that this Q is turning out to be 0, and for this one, this is actually is equal to minus 1. And the same check you can do for ER. Remember that we said that the reason that we could embed electromagnetic interactions in this whole picture was actually to have T3 YR is equal to minus 1, because T3 of ER is equal to 0. So this is actually equal to so that the charge of right-handed electron is also minus 1. So this brings us to the summary of weak and electromagnetic interactions. So basically you have the kinetic terms, and then you have the charge current interactions with electrons and neutrinos, the photon interaction with electrons, then you have the both neutrinos and electrons interacting with the Z in the form of CV minus CA gamma 5, and then these are the kinetic terms associated with the gauge bosons. And these are the Feynman graphs that you have. These are the couplings of the electrons and neutrinos with the gauge bosons, and these are the gauge boson self interactions. And once this electroweak Lagrangian was established, there was a very important Nobel Prize to Salam, Glashow and Weinberg. So now we are in a position to revisit this electron positron annihilation. So basically you have photon mediation, but you now know that there is a Z mediation here. So, therefore, when you compute the matrix element squared, you have to take both these things in together, and once you compute the annihilation cross section, you can now see a beautiful Z peak here around this point, and that led to the discovery of the Z boson. But at the same time, there is also very importantly, we could actually explain the forward backward asymmetry once we took the interference with the Z mediated interaction. So, that asymmetry in the differential distribution could also be explained. So, then we have the strong interaction or QCD. We are not going to elaborate too much on this part. Basically, it is a similar exercise that it is also a SU3 gauge theory, and basically now you say that only quarks feels that they take part in this kind of strong interactions, and so the transformation has to be just aided with the SU3 generators, which are the TAs, which are the Gell-Mann matrices, and you do a similar exercise like changing your usual derivative to a covariant derivative, which has this piece with generators associated with the gluons. There are 8 gluons corresponding to this SU3, and then you can find out the interactions of the quarks with the gluons proportional to the strong interactions. And of course, these generators are 3 cross 3 matrix, so Q must be a column vector. So, there are 3 colors associated with the quarks, and some people call it red, green and blue in this particular assignment. And then you can write the QCD Lagrangian also, and you have the Feynman rules for the QCD very similar to the electroweak Lagrangian that we had. The only difference between the electroweak and QCD is the point that the quarks do not exist freely in nature. They always form these bound states called baryons and mesons, and they form this kind of jets once the QQ bar comes out. So, in a very similar way that we calculated E plus E minus to mu plus mu minus, you can calculate E plus E minus annihilation to 2 jets, and the only difference is that when you calculate E plus E minus to mu plus mu minus, it is as simple as 4 pi alpha square by 3s, whereas for 2 jets, this is simply multiplied by a factor of 3, and this factor of 3 comes because of the color, and there is another factor which is q square, which are essentially the charges associated with the quarks, and this is something which is experimentally verified. So, this together with another fact that QCD coupling also runs, and the running is actually dictated by this particular formula and this kind of graph which you actually could probe in the experiment. It was actually proved that SU3 gauge theory is a good way of representing perturbative QCD, and then there was a Nobel Prize in 2004. So, this actually completes the standard model that it is basically a C3C cross SU2L cross U1Y gauge theory, and this is the full gauge Lagrangian associated with the standard model, which has all the pieces of all the fermions, all the field strength tensors, etc., etc. I mean, which I do not need to repeat any further. However, the only thing that is still missing here is the mass terms associated with these fields. And for that, what we require is called the spontaneous symmetry breaking. So, it is easy to understand that mb square b mu term you cannot write explicitly, just simply because you have a transformation for b mu which is like b mu prime equal to b mu plus del mu chi. That makes this kind of term non-invariant. Fermion masses are not allowed, just because we have already seen that the left handed, because whenever you try to write the mass term associated with the fermion like psi bar psi, they will actually mix the helicities, like it will be psi L bar psi r plus psi r bar psi L, and because we know that the left handed components form a doublet and the right handed parts forms a singlet, this is not also invariant under the standard model. So, therefore, neither the fermions nor for the gauge bosons we can write the mass terms. So, therefore, what it is what is apparent that we must break the SU2L cross U1Y symmetry in somehow, so that we can generate the adequate mass terms. Now, how do we break it? We actually keep the SU3 symmetry intact, and this SU2L cross U1Y symmetry breaks to a remnant U1 electromagnetism. Now, why it is so? This is because this unbroken gauge groups, the corresponding gauge bosons remains massless, because that is how we see it in nature. Gluons are massless and also photons are massless. So, therefore, the symmetry breaking, which will generate essentially the masses for all the quarks and leptons, and only for W and Z boson masses, keeping the photon massless. Okay? So, that is why the symmetry breaking actually has to occur in this particular way. So, this brings us to this interesting possibility of identifying what is called a Higgs boson. So, in the standard model, you basically have to introduce a scalar isodoublet with hypercharge plus half. And so, therefore, what basically it means that it's a matrix with 4 real degrees of freedom with 2 complex entries, essentially phi 1, phi 2, phi 3 and phi 4. And you can also find out that if y is equal to plus half, following our exercise that we did, that q is equal to T3 plus y, we can simply write the associated charges for the up type component and down type component, and it is simple that this is plus half is equal to plus 1 for the up type component, and for the down type component this will be minus half plus half is equal to 0. All right. So, then you want to write the SU2L cross U1Y gauge invariant Lagrangian involving the Higgs field, and this is how you should write. So, there is a kinetic piece with a covariant derivative acting on the Higgs field, and this covariant derivative is del mu minus Ig W mu A sigma A by 2 minus Ig prime half B mu. This half is associated with the hypercharge of the Higgs field that we have already assigned, and then there is a scalar potential. Now, the gauge invariant scalar potential for this isodoublet can be written in terms of mu square phi dagger phi plus lambda phi dagger phi whole square. And if we keep mu square greater than 0, then there is no non-zero vacuum expectation value, but if you have mu square less than 0, then there is a non-zero vacuum expectation value. And the Yukawa interactions are the part which actually connects the Higgs field with actually the corresponding leptons and quarks, and these are the possible ways of writing the gauge invariant Yukawa interaction. So, you have LL bar phi ER plus the conjugate. For the down type quark sector, you have QL bar phi DR, and for the up type one you have a phi C, which you can define simply as minus I sigma to phi star. So, this is the complete Lagrangian associated with the standard model Higgs field, and once you do now minimize this scalar potential del V del phi equal to 0 for this kind of a potential with mu square less than 0, you get 2 solutions. One is phi equal to 0 and the other is phi dagger phi equal to V square by 2, and this is basically the phi dagger phi equal to V square by 2 gives you infinite number of degenerate minima in the scalar potential, and once you choose a specific position in the minima, then you basically break the symmetry spontaneously, because the parent Lagrangian still preserves the symmetry, but the vacuum that you choose your theory to expand upon breaks that symmetry. And this is usually the way that we choose our vacuum, that phi is equal to 1 by root 2 0 V plus Hx. So, and this little Hx is what we call the Higgs boson. Okay, so once we have the Lagrangian and all the ingredients, all the interactions, we have the Higgs interaction partices, the Higgs to gauge bosons, you know, 1 Higgs to 2Z boson, 1 Higgs to 2W, 2 Higgs to 2Z, etc., etc. And this essentially arises from the kinetic term. And secondly, we have the Yukawa interactions of the Higgs with the fermions, and this comes from the Yukawa terms for sure. And all these vertices are proportional to the corresponding masses. And then we importantly have the Higgs trilinear and quartic couplings, and this what is called the Higgs self interactions. And these are very important vertices which are still being probed, and this is something that we come back in context of effective field theory as we go along. Okay. So, particularly the measurement of this trilinear interaction will actually confirm what kind of Higgs that we actually have. So, then it was the Higgs discovery at LHC. Maybe I can talk briefly about that, that there are several Higgs production modes. You remember that the Higgs actually couples to the fermions proportional to its masses. So, there is no tree level single Higgs production mode excepting for via this one loop graph. So, the gluon via top loop, I mean dominantly produces Higgs, and then there are this vector boson fusion processes. This is the Higgs Tralhong with WWH production, and then it can also be produced along with TT, etc. So, there are different production modes in context of LHC, and then there are several decay modes of the Higgs boson depending on what mass that you choose for the Higgs, and that we do not choose, the nature chooses, and that is what experimentally we found out. So, this is the experiment where you can see that it was searched via I think it was via this is 4 lepton, right. So, this was via which channel WH channel, perhaps this one. Yeah. So, the invariant mass of the final state, or ZH perhaps, and then you see that this is the standard model background contamination, and here is your signal, and which peaks here, and that gives you the discovery of the Higgs, and it was another Nobel Prize which actually followed, and I think this is the latest one in particle physics to Professor Peter Higgs and England. All right. So, with this we are end of this lecture, and so basically we have a very nice model which is the standard model, which is well known and which has been tested in several experiments to highest degree of precision, I mean to very great degree of agreement. So, the standard model is complete, but there are several issues that provokes us to look for physics beyond the standard model, and some of these issues are like generation of neutrino mass, which I will talk about in next lecture. Then the issues associated with dark matter, the stability of Higgs vacuum is also a issue which I do not know whether we will be able to touch upon or not, and there are several others. There are many other things that one can talk about, like the hierarchy problem and so on. So, the point is that although standard model is very well tested theory, I mean it is not yet perhaps the complete description of nature, and there are several reasons that we should study physics beyond the standard model, and the way or the approach that we take will be actually using effective field theory, which Jose has already introduced you, that assuming that we are still lying below the scale of reaching to the new physics. I mean our energy at LHC is not enough yet to reach to the scale where we can probe that new physics directly. We would like to see whether there are deviations in the signal spectrum because of the presence of those heavy new physics. So, this will be our approach. So, with that I think I will conclude here, and I apologize for all the kind of confusions and regarding the slides and etc. Hopefully, it will be fixed from tomorrow. Yeah. Thank you so much. And I will be happy to take up questions if you have. I think this part is all known to you, so therefore it's kind of obvious. I mean EFT to show up means, see the point is, okay, so you are saying that a minimum deviation from the standard model prediction. I think it's a TV scale. I mean, there are issues with LHC. I mean, when you are trying to probe EFT at LHC, there is a big fear because it's a hadron collider which has energies of 14 TeV. Now, ideally, when you want to prove an effective field theory at a collider, in principle your center of mass energy should be less than the new physics scale. So, in that sense, if you have to really talk about effective field theory at large hadron collider, that makes your new physics scale as heavy as 14 TeV. But the point is, it is not necessary to have the new physics scale that heavy, simply because of this thing that whenever you produce, suppose you are producing Higgs Tralong and there is an effective operator contribution or effective theory contribution to this Higgs ZZ Higgs or WW Higgs Bartitz, or it is giving you some new 4-point interaction. Then what you can do, that you can plot the invariant mass distribution of whatever final state that you are looking for the signal. Now, if the distribution of the signal, peak of the distribution is lying below the lambda that you have assumed to produce that signal, then you can say that the bulk of the production essentially has happened less than the LRG scale associated with the new physics. So, in that case, therefore, at LHC, I think we can still, it's very case dependent, like what exactly is the new physics contribution that you want to probe. Like if you want to probe the Higgs physics effective scale or effective operator contribution, I think it is still possible to have a TeV scale new physics. But suppose you want to probe trilinear gauge coupling, then the energy scale associated with it will be way heavier. So, this depends on the kind of process that you are interested to probe. More questions? Okay, if not, then we break for lunch now, and we assemble here at 2:30 with the second lecture by Jose, and then then we will have a tea break, and after the tea break we will have the guest lecture by Joydeep. Okay, so that's the way that we go. Thank you.
Hello? 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 1, 2, 3. Hello? 1, 2, 3. Hello? 1, 2, 3. Hello? 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 Hello, test. Hello, test. Hello? Munmi?
2 minutes. All right, let me begin. Welcome back. So let me remind you quickly, the one big thing to take away from the lecture this morning was this prescription on how to construct the effective Lagrangian, and to understand the limitations of the formalism. Without that, one is prone to get some errors out of the calculation. Excuse me. What I want to tell you during this lecture is two things I want to cover. One of them is the decoupling theorem. The decoupling theorem is the formal result that justifies the expansion in inverse powers of a heavy mass. I will not derive the result here. I will give you a reference because there's no time, and it's a technical calculation that requires the choice of a specific regularization technique. Doing it right, it's involved, so it takes time. And also, I would like to cover a little bit the role of gauge invariance in effective theories. I argued that you cannot have an effective theory that is gauge variant only, say, in one operator, because the thing propagates, and I'll review that. But there's a certain aspect of gauge invariance that I think will be interesting because it illustrates the physical content that gauge invariance provides to any given theory. Now, the actual length of this lecture, of these two topics, is, I don't think, I think I will finish slightly before the time allotted for this during this hour. So in that case, I will start with the very beginning of the next lecture, because it will give me a little bit more time. Well, because there are other lectures that have much more material, and so I might spill over or begin the next lecture at the end of this one. All right. With that, let me ask if there are any questions about the first lecture. Okay, if not, let me begin. So the decoupling theorem, and as it says here, without proof. And the idea here is that one has a theory, a full theory, with two types of fields, a light field and a heavy field. And the Lagrangian can be separated, or the action can be separated into two terms, one that involves only the light fields and it's renormalizable. And this is a heavy, I denoted as H for heavy, that involves both the light and the heavy fields. Just as for the example I covered in the morning, one can define kind of an integrated effective and I'm going to call it effective-ish Lagrangian action for reasons that will be clear below, by integrating out the heavy guys. And this is done, again, in the same spirit as in the morning, that we will not have enough energy to produce real phi's, but we can certainly probe the virtual phi, capital Phi effects. Now, if you're interested in the proof of what I'm going to tell you, it's in the nicest proof I've seen. It's in a book by Collins, by John Collins. It's called Renormalization. It's very readable. It's in chapter 8. Okay. So the result of this, of the calculation, of doing this integration properly, is the following. This S prime has two terms, one that are divergent, and one thing I forgot to emphasize, I'm sorry to say, the fact that SL is renormalizable is actually important. In our case, in the cases of interest that we'll do, the standard model, that is not a problem. This will be the standard model Lagrangian, which is renormalizable. This would be something else. If you like supersymmetry, this would be the supersymmetric part of the Lagrangian. It has all the superpartners in it. The fermionic superpartners, say, for example. And this could be the standard model with another doublet. So two doublet standard model, and then all the superpartners here. And what you do is you imagine a situation where all the superpartners are heavier than the energies available to one, and one gets this S prime by integrating them out. This S prime has two terms. There's a divergent contribution, and then the finite part is what I will call the effective action. Because this is a divergent contribution, or not because, but it is unobservable, and in fact, part of the proof, and the hard part of the proof, is to show that in fact, what it does, it renormalizes the coefficients in SL. So a renormalization of SL absorbs all the divergences that are produced by integrating out the heavy fields. If you actually do the calculation, you will find that there are divergences that are proportional to positive powers of this lambda, or the heavy field mass. And you might say, well, gee, that when you do the calculation, say, this is a problem. I'm finding terms that don't drop, as I said earlier today, don't drop when m is very large. But on the contrary, they increase. But those terms are not observable. They are renormalization effects that we just absorb into the coefficients of SL. And then, again, the last part of the proof is that for large lambda, the scale of the heavy fields, phi, the scale of the heavy fields, the S effective can be written as a series with in 1 over lambda with operators OA that, since I've integrated the heavy fields, are made out of only the light fields. These coefficients CA are finite. OA is a local operator in the light fields F. And in particular, all observable effects of the heavy physics disappear, decouple, from when the scale of the heavy guys goes to infinity. And this is done for, without any, this can be proven for basically any theory that you have, which is renormalizable. Okay, that's kind of thing, any renormalizable theory. And the condition that SL is renormalizable in the phi fields, and this whole thing is renormalizable for the light and heavy fields, is not one you can dispose of. If that is not true, then the theorem is not true. It's an important assumption or requirement.
So the renormalizability of SL and the whole...
What do you mean?
The normalizability of SL comes into the fact that this statement that you are writing, that
well, actually, that's what happens. Absolutely. So the comment was that the renormalizability of SL ensures this is the case. Mm-hmm. If SL is not renormalizable, what happens is the heavy, upon integrating, that is, if SL has terms, is missing terms, you just don't write them down, or for some reason, then when you integrate out the heavy guys, it will generate, that integration process will generate the terms that you're missing, and they're infinite, they're divergent, and you don't know where to absorb them. And that's why SL must be renormalizable.
Jose, another point, that when you find out that S prime, does not that include SL? S prime?
S prime, not necessarily. Well, what happens is, not necessarily. What I'm sorry, the comment was, it disappeared. So the comment was that, why do you need SL to begin with? Doesn't it generate? Is it not generated by the integration procedure? So S prime will contain SL. Indeed it will, but the problem is the coefficients are infinite. You need to have a coefficient that you can use to eat up the infinities. And so then that's what happens.
No, my question is in particular about the last statement, that when your lambda tends to infinity, shall S effective go to SL or S effective?
No. Remember, the S effective is the finite part that results from integrating out the heavy guys. Okay. So it's not the whole thing. So the total action is S effective plus SL. Okay. So basically what it says is, in these conditions, if you assume hypothetically that all the heavy physics is infinitely heavy, then you see absolutely nothing but the light theory. It just guarantees that case. If any of the assumptions that I mentioned is violated, then the result is not true. It's not true. So, okay. So that's an important thing. Okay. Again, this is useful because it justifies the expansion to all orders. From the proof, you also find that if SH, the heavy guy, is invariant on the symmetry that involves only the light fields, then S effective inherits that symmetry. That S effective can certainly be used in doing loop calculations, but again, this is an effective theory that assumes that you have integrated out heavy modes of order lambda. If you just put a few of the terms of S effective into your loop calculations, then you're assuming tacitly that you are not able to see the heavy guys, and somehow you must restrict the formalism of doing loop calculations to energies below the scale of the new physics, because you've assumed already that you don't see it.
But just one thing. So in the loop, I mean, those heavy particles can appear, right?
Okay, so what happens is, so the comment was, but in the loop the heavy particles can appear, of course. But so here's the thing. If you do a calculation with the full theory, in the heavy particles, you put the propagators, and you do the calculation, and you're done, right? If you do it with the effective theory, you're not doing that. What you're doing is the propagator, instead of being 1 over p squared minus m squared, you're expanding the propagator. And the propagator becomes 1 over m squared plus p squared over m squared plus p to the fourth over m to the fourth, blah, 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 blah. If you put them all in and sum it and then do the integration, nothing happens. But that's not what we're doing. We put one term, another term, and then you will get funny divergences that are not physical, because you've assumed that you're at energies below lambda squared. And so somehow you have to ensure that the loop calculations comply with this assumption. In practice, we just put a cutoff. But for students, you should know that's usually problematic. Putting a cutoff saying that p squared is less than lambda squared is not can generate problems with Lorentz invariance. And so that should be done with care. There's ways of putting a cutoff using regulators like polyvillars. regulators that fixes the problem, but that require, if you want a rough and dirty estimate of an effect, cutoff is fine. If you want to do a very careful calculation, then you should think about how you're going to impose a cutoff and do the renormalization. Okay. Divergent pieces that you get in doing calculations are not observable. Lambda is a physical quantity, so you're imposing a physical cutoff on the integration. And if you regularize the integration using whatever method you want, the regulator is not lambda. Yes, sir?
So the SH is invariant of the symmetry. Is it the requirement of the proof?
It's a consequence of the proof.
Okay, consequence.
It's a consequence of the. Okay. So the comment was whether this is this thing about the symmetry, whether it's a requirement of the proof. And the answer is no. If the SH is invariant, if that happens, then that invariance, that symmetry is inherited by the effective theory. Okay. So, for example, if you have a grand unified theory, and you segregate the standard model modes with all the other modes, then, I don't know, you have your big group is SO10 or something horrible, right? But this SO10 inside has SU2 cross U1 cross SU3. It's in there, right? So the heavy guys have this U1, SU2, SU3 symmetry of the light guys and other stuff. The other stuff doesn't go down. But because the light guys are invariant under SU2, 3, and U1, then the low energy theory you get, the effective theory you get by integrating the heavy guys will have the standard model symmetry in it. Okay. All right. That's the decoupling theorem. It basically justifies the expansion that I roughly argued and hand-waved about earlier in the day. The other thing I want to talk about is gauge invariance. So, in all the extensions, if you do any calculation with grand unified theories, supersymmetric, anything, any concrete model that you might want extension of the standard model, you'll find that the theories have a grand or large total symmetry group, and the standard model group is embedded into it. It's part of it. It could be the same. Like, for example, in the minimal supersymmetric standard model, they're the same. But G tot can be larger. And as I said, from the decoupling theorem, you find then that the OA are invariant under GSM. Because this is a subgroup of the total group. And this is what happens if you choose particular groups. But it might be interesting to ask what happens if you decide that, well, there might be something else that doesn't obey this, what I'm saying, something else, that some kind of new physics where the OA might not be invariant under the light gauge symmetry. What would happen in that case? What would be the consequences? And as I mentioned, to just describe this in pictures, you add one gauge variant term, and then when you do radiative corrections, this gauge variant term gives birth to all the other gauge variant terms that you can write using the light fields. It propagates. And so you might say, okay, done. Like I get a non-unitary theory, I stop, so I don't include this guy because I get a result that's not physical. And that's fine. But there is an aspect of this thing about gauge invariance that came up a few years back that it's worth looking at, not necessarily because it might be really interesting in itself, but because it illustrates the physical content of gauge invariance, I think, a little bit better. And this goes under the name of the Stuckelberg trick. Stuckelberg was a a well-known father of quantum field theory in the 50s and so on. And he realized the following fact that, or the following procedure that can generate a gauge invariant theory from any theory. It doesn't matter what it is. So I'm going to ask you to imagine that you have a theory, which is not a gauge theory necessarily, but could be, but let's imagine it's not necessarily a gauge theory, that has a bunch of gauge, of vector bosons. These are not, in principle, gauge bosons of anything. And n can be anything, can be 0 or can be 200, I don't care. And aside from this these vector bosons, you have other fields, chi. And chi are scalars, fermions. No? If you are really adventurous, anti-symmetric, tensor fields, anything you want, no? Something else. With a chi. And there's your Lagrangian. It depends on the w's and on chi. That's it. And there's no gauge symmetry. But what he realized is that there is a way, a procedure, for interpreting this as a gauge theory in which this expression is the version of that gauge theory in the unitary gauge. And let me tell you the story of how that happens. So what he said, what I tried to emphasize, originally these n vector bosons are not gauge bosons, but he said, let's assume they are. So I will choose any Lie group of dimension L, which is greater than n. N is the number of these guys. The number of n these guys. And this group can be anything. Can be U1 to the L, or whatever thing that has more than n guys. And they're generated, and the generators of this group I call Tn, which I choose to be anti-Hermitian and normalized in this way. Standard thing. If you don't like this anti-Hermiticity, you can choose them Hermitian, and there's an I that shows up someplace else. If you don't like this normalization, you're welcome to change, and just changes the definition of the gauge coupling cost. It's just not. First thing, then you complement the original guys, but by a bunch of non-interacting vectors, W and mu, where little n goes from n plus 1 to L. You might choose L equal to n and be done, but it might be that, I don't know, that for some reason you really like SO32. And your theory doesn't have enough W's to meet the dimension of SO32, which is 32 times 31 over 2, whatever that is. And so you add the discrepancy and you put them in here there. And you put them in, how can you make them non-interacting? It's very easy. You add to this Lagrangian terms that go like kind of the F mu nu, the field strength tensor of each one separately, W mu nu n, for n equal to from here to here, and you square F mu nu n squared, you add them all up. And you want to add a mass for these guys? No problem. W and mu times m, and you sum them all up. The only thing I want is for these guys not to talk to anybody. Okay? That is, they just talk to itself. Right? Not between themselves either, just to itself. All right. So now I have an extended Lagrangian, has non-interactive these guys and the original terms that interact, and I define a derivative operator that looks familiar. It is a covariant derivative. It has the d mu, it has the w's and has the t. Another thing. And next comes the creative part of the proof from Stuckelberg. I can say anything. So what he did is he introduced a unitary field, U. It's an auxiliary unitary field. Oh, I'm sorry. Before I go, let me emphasize the W's will become the gauge fields of this gauge group, but the chi's do not transform at all in this construction. They are singlets under this construction. All right. He introduces an auxiliary unitary field, that is U times U dagger is 1 in the fundamental representation of G. That is, it does transform, in contrast with the chi, this U does transform under the gauge group, and it transforms like this. This is the fundamental, how the fundamental group representation transformed. Some of you might miss a factor of I. It's not there because I've chosen the Tn to be anti-Hermitian. It's just that. This is the only, let me emphasize, the only field, aside from the W's that are the gauge fields, this is the only matter field that transforms non-trivially under G. The chi's are trivially, they don't behave, feel, if you wish, any G transformation. And the last part of the construction is to define these objects, W and mu. This is Tn, this is a generator. This is a U dagger. This is the covariant derivative. This guy. Acting on U. This. And you take the trace of it. And the last part is everywhere that you see, there are as many curly W's as there were straight W's. So you can replace, wherever you had a straight W, you can replace a curly W and put it like this. Now, because this U transforms like this, and because I've assumed the straight W's, now I reinterpreted them as gauge bosons, this object here turns out to be gauge invariant. It's a gauge invariant object. Second, if I take the unitary gauge and replace this U by 1 and look at the normalization, in the unitary gauge, U equal to 1, W, curly W, becomes the straight W, everything. So you have a gauge invariant theory, because this is now gauge invariant. This has been gauge invariant always. But you have a gauge group, you have gauge transformations, you have all the things you expect in a gauge theory. And in the unitary gauge, it reverts to your previous guy. So this process creates for you a gauge invariant theory out of any theory. It doesn't have to be gauge invariant to begin with. You just reinterpret the vector fields as gauge fields. You choose a group big enough to eat them all, and then you introduce the auxiliary field U to ensure that gauge invariant is maintained. It's auxiliary because you can, by this virtue, you can always choose a gauge where U is equal to 1. It's always can choose a gauge where U is equal to 1, so that's possible. And then in that particular gauge, in that unitary gauge, you recover your original Lagrangian. Ta-da! You might say, well, then what's the point of gauge invariant? I can take any theory and make it an invariant theory. So what's the point? Good. Okay. I'll tell you what the point is. Okay. It's true that you can take any theory, make it and invariantize it, right, in this process. But it is not all. Well, it has its problems. Let me tell you what the problems are. We'll come to that in a second. So this is, I'm just recapping what I said. NEL becomes some gauge invariant theory in the unitary gauge. So why should we require them to be gauge invariant? Before I continue, let me just note that the group G is arbitrary as long as it's big enough to eat up all the W's you started with, but it's the same group everywhere. So if you have one operator, that's invariant under group G, and you have another operator, that's invariant under G prime, it must be that G is equal to G prime. You cannot choose different G's for different parts of the Lagrangian. That's really not allowed. So, for example, if your terms in the Lagrangian that have dimension less than 5 have the standard model group as the symmetry group, as the local group, then all terms would have to be standard model invariant. But the standard model has what? Has a W plus W minus Z and photon 4. But you can choose, using this thing, any group that has dimension 4 or larger, and go through the procedure, and you get some gauge invariant theory with a unitary field, and that's it. You change the thing, right? That's how it goes. There's no need to have a gauge invariant requirement, apparently, at the beginning. However, as I've been emphasizing, the matter fields are all gauge singlets. And in the standard model, that is not the case. Absolutely not the case. So because they're not gauge singlets, you get lepton universality. The electron, the muon, and the tau couple the same way to the gauge to the gauge fields, to the W's and the Z's. This would not be the case in this. This would be totally accidental within the construction that I mentioned. Because the couplings to any field, to any other field, are arbitrary. You just have to be, maintain Lorentz invariance, right? There's no reason why the electron and the muon should have the same coupling to the Z. So all these are completely accidental. The masses of the gauge fields are unrelated. So the famous relationship in the standard model that connects MW/Mz to the weak mixing angle would have to be an accidental result. Okay? And so these great successes of the standard model, one of the reasons we believe the standard model, one of the big reasons, is that it predicted lepton universality. It predicted this relationship that was later observed experimentally. And so it gave rise to this understanding. But inherent in deriving this thing is the assumption that the matter fields, chi, do not transform trivially, or transform non-trivially under the gauge group. And the last thing is, you notice this is a unitary field. This is not your regular field. It satisfies a constraint. U dagger U is 1. That is not something you find usually in the standard model. In fact, you don't find that type of constraint in any renormalizable theory, because such theories, those that include this type of unitary fields, are not renormalizable. Again, in this case, what that implies is that the theory becomes strongly coupled at a relatively low energy. This is not the standard model W. This is the W's, the masses of the W's that I've been talking about. Beyond this thing, this type of the energies of this sort, we cannot calculate. We just don't know how it happens. We don't know what the theory is like. The standard model does not have this problem. The standard model works very well, as far as it's been proved at the LHC, at energies above, or even those just slightly above 3 TeV. There's no indication that the standard model has any strong interactions, aside from QCD. But QCD is asymptotically free, so at energies of this sort, you have a weakly coupled theory. There's no indication that there's any effects. This theory would fail in predictability at this type of energies. So standard model gauge invariance does have does have content. In gauge invariant does have content. It predicts relations between the couplings of the matter fields. It predicts couplings, relations between the vector boson masses. And it allows weakly coupled models, which seem to be, or weakly coupled physics, which seem to be the case that we have to, that we're dealing with. That's what seems to be the case from the physics we observe. So it is true that this Zuckerberg trick is interesting, right? In that you can change any theory into a gauge invariant theory, but one should separate interesting from phenomenologically relevant. So the Zuckerberg trick is interesting, but it's not phenomenologically relevant. Gauge invariance is important. The light theory should satisfy the standard model gauge invariance, and therefore the effective theory should do that as well. And the matter fields involve the light fields that we're dealing with, in this case, the standard model matter content, all transform non-trivially under the gauge group. Any questions? This finishes this part of the thing, and I'm about halfway down the lecture, so I have time if you have any questions. I was as obscure as that. Okay. Yes?
Can you go to the last slide?
This?
Yeah. So can you elaborate the last point?
Oh, okay, so explain this part, right? Explain this part, yeah. So what happens here is the following. You can take this guy here. How do you derive it? Let me tell you. I'm not going to derive it. I'm just going to tell you how to derive this, okay? All right. So you can look at this guy. This guy depends on what? It depends on the sky guys. It depends on the W's that are buried in here. And it depends on U, okay, on this U field. Now, what you can do is you can write U. Let me see if I can do this here. Now oh, it has to be right here. Nope. What happens if I do this? Yeah. Okay. Page up. Yes. Then, can I write? No. I can't write. Anybody? Do you know how to write? Okay, I stop. So what I'm going to do is write out the exponential field, the U field, as an exponential. U will be e to the I something, okay? And what I'm going to look is that I something at the top. I am going to, well, it's a field. It is a Hermitian field, and I can use it to do, I can do calculations with it, okay? I'll explain it a little bit in a minute. And what I'm going to do is scattering of the fields in the exponent. I'm going to tell you about scattering the fields of the exponent. So bear with me, okay? So Shubha, maybe for next lecture I do need a blackboard. It works? It's it? Okay. Okay. You know the story, right? NASA spent $1 million developing a pen for them to use, for the Apollo people to use, to write down. Because if there's no gravity, the ink doesn't fall down, right? And $1 million. You know what the Russians used? A pencil. Okay. Does it work now? I can. Okay. So going back, so I'm going to write the U field. No, okay, I can't write. I can draw. I need to draw. There you go. Okay. I don't know how, I'm not going to try to erase. I'm going to write back here, okay? So I'm going to write the U field as e to the I pi. 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 Okay. All right. And this pi is Hermitian. This ensures that U dagger U is 1. Okay? And pi is like a sum of pi n and pi n t. Oh, I'm writing too fast. That's what happened. N. Nope. T n. Okay. Like I'm having a stroke. So I'm sorry. So you have to think of this as pi n Tn, okay? All right. And these pi n's are Hermitian fields, okay? And you can ask yourself, what is the scattering cross section for pi pi to pi pi? You can do that. I mean, you can do that. There are many terms, many terms. But because this term here, this guy here, has an exponential. So let's see. Let's go through this thing a little bit. Let's say U dagger is e to the minus I pi. Then this has term, but one of the terms here is d mu u. Okay, that is, if you expand in terms of pi's, what you get is powers of pi and one derivative of pi. That's what you do from this thing. So among the many terms that show up here, you have terms that have many pi's and one guy with a derivative of pi. Yeah. When you put this thing in here, you will end up with terms that have many pi's and the derivative of pi squared. You will get that from the w, curly w squared. You have those terms. Okay? And so those are vertices that involve only pi's. And you can calculate using those vertices the scattering of pi to pi. Okay? And it turns out those scattering terms increase with the center of mass energy. Okay? And so with the center of mass energy sufficiently large, the scattering cross-section will become sufficiently large to violate a unitarity limit for quantum field theory. Unitarity is lost, and you have a strongly coupled theory. Okay? Now, the reason I say you have a strongly coupled theory is like I told you, I don't calculate infinite contributions to this. As I said, there are many contributions to the scattering. I calculate the simplest one. It violates unitarity. And I calculate the next order one. It also violates it, and it's of the same order as the first one I calculated. And so all the terms that I calculate will be of the same order, all violating unitarity. Now, what happens, really, I don't know, because I would have to sum them all up and see what I get. But I can't. But the fact that higher and higher order terms contribute the same amount to the cross-section is a telltale signal that you have a strongly coupled theory. Okay. And that's why you do that, yeah. And I hope you appreciate the art. Other questions?
Just one quick thing is that, I mean, how is there any restriction on the number of chi fields that you can associate with? There is apparently no such restriction, right?
No.
You can, introduce as many singlet fields as you want.
Do you mean these guys? Yeah, as many as you want. You can add as many as you want. I mean, as I said, if you have 4 gauge bosons, but you really like SU 73, then that has 73 squared minus 1 generators.
That is for the gauge fields, but for the chi fields.
No, they're just sitting there.
Such,
As far as gauging variant is concerned. But instead of having, for example, the neutrino and the electron be in a doublet, there's no reason for that to be the case.
Correct.
So you have an electron field and you have a neutrino field,
Correct.
and that's it.
Yeah.
Right?
So it can be a hidden sector kind of theory.
Yeah.
I mean, you can.
Yeah, it kind of thing. But exactly. So there's no question. Other questions? Okay, if not, let me move on to the next lecture. Okay. And it is to talk about cases where there are non-decoupling situations. Okay. I'm not going to cover this in great detail because the examples of that the course envisions, neutrino physics, Higgs physics, dark matter physics, they're all decoupling situations for the cases I'm going to consider. So this will be kind of an aside. But I think it has interesting aspects that will be useful. And so what do I mean by non-decoupling situation? So the decoupling theorem, as I said, guarantees that when the scale of the heavy guys goes to infinity, all the effects of the heavy guys disappear. All observable effects of the heavy guys disappear. But there are situations of interest where you want to consider theories below some scale, but that scale doesn't decouple. That is, if you increase the scale of the heavy modes that you don't want to look at, then the effects don't go away. In fact, you know one such thing. So imagine the standard model. You had the standard model, and forget about the fermions. Okay? Standard model, gauge bosons, and the Higgs. And what I want you to imagine is a situation where the Higgs is very heavy. It's so heavy that the LHC cannot see it. Okay? So very heavy Higgs. And you ask, well, it just decouples, you just erase the Higgs. But that is not the way it works. Bad things happen if you erase the Higgs. Why? Because, think about it, the Higgs mass is composed of two factors. One of them is the coupling constant in the potential. Lambda, let me call it little lambda, it's coupling constant. And the other is the standard model VEV, the vacuum expectation value. Now, I want to make the Higgs very heavy, but there's two ways of doing this. Well, three ways. I can make lambda and V very large, or I can make lambda large and keep V steady, or I can keep lambda steady and make V very large. Okay, if I make any of those that has V very large, has two effects. Makes the Higgs very heavy, and makes the W and the Z very heavy. And since I told you that, that there's no fermions, you're left with photons. A very boring theory. And that's not what we're looking at. We're looking at a situation where the W and the Z can be seen, produced, and the Higgs cannot. And this was the situation at LEP. It was not, this is not such a far-fetched situation. Okay? You're too young for LEP, but trust me, people like me were alive, and we saw the actual experiment happen. It didn't have energy to produce the Higgs, but it had energy to produce W's and Z's. Okay, so how do you make the Higgs heavy? Is you make lambda heavy, little lambda heavy. This is different from the decoupling case. In the decoupling case, there was a scale, thing with dimensions, that went very large and the effects went away. In this case, you have a coupling that's becoming very large. When couplings become very large, well, some masses might increase, but the interaction strength also increases, and you end up with a strongly coupled theory. In fact, what happens in the standard model when you make the Higgs very heavy is you get a theory that has W's and Z's, and if you like the fermions, you can bring them back in. They're all in there. No Higgs, but the theory is strongly coupled in the bosonic sector, and becomes the radiative corrections become too large to manage, in the sense that first, radiative corrections are of the same size every time you do a next order, so they're all the same size, precisely at this scale. And I'm not going to go through the details of that, but the reason is exactly the same. There will be a unitary field, and that unitary field you can calculate scattering, and the scattering becomes very large, violating unitarity at scales of the order of 3 TeV. So if you make the Higgs heavier than 3 TeV, the theory becomes strongly coupled at 3 TeV. And so, so there's a difference in that in one case, the decoupling occurs because a dimensional scale is assumed to be very large, or is very large. In the other case, the decoupling occurs, or the heavy masses occur because a coupling is large. And that is different. So dimensionality counts in these considerations. So I'm going to look at such cases, not all of them, but some cases where there is no decoupling. That is, heavy masses occur, large masses, because of a large dimensionless coupling. Okay? Along the way, I'm also going to talk about the decoupling case to compare and contrast. Okay. To do that, the way I'm going to present it is to go back a little bit. And if you remember this morning, I talked about hierarchies. That is a way of ordering operators into leading, subleading, sub-subleading, and so on, such that the contributions, the observable contributions of the leading ones are much larger than the subleading ones, much larger than, those are much larger than the sub-subleading ones, and so on, so that eventually one group will be unobservable. The effects of the groups and beyond, one point beyond, will not be observable. And the number of operators in each group, leading, subleading, and so on, is finite. So I'm going to do a characterization of this, of a way of imposing or describing this hierarchy that will be convenient. So this will look a little bit abstract or unmotivated. And the reason I'm not able to motivate it is that I don't have any real good reason behind it. It just works. You see, this is something that occurred to me, and it worked. And I thought it's a good way of summarizing several different types of effective theories. And so instead of going through each one separately, I can do it all in one fell swoop. So I'm going to define a property of an operator, just a number associated with an every operator, that I'm going to call the index, and I'm going to call it S. Okay. And so for an operator that has little d derivatives, and b bosons, and f fermions, and the gauge bosons are buried in here in the covariant derivatives, I'm going to define this index of the operator S that depends on a real parameter u, which is not defined at the moment, just a real number, and it has this funny thing. And here, again, I apologize, it just works. It's useful because it works. I cannot reconstruct how I came up with this, but it's a useful thing to consider. You can rewrite this ugly-looking thing into a slightly less ugly-looking thing, like this. Has two terms, which I call delta. This has no little u in it, it's just delta. This is the mass dimension of the operator minus 4, delta. And multiply, adding u minus 4 over 2 times the number of matter fields minus 2. That's B matter field, F matter field minus 2. Okay, that's the definition of it. And my job is to try to convince you that this funny and contrived formula has some uses. Okay, so I am going to use this index to say that O leads O prime. So O is more leading than O prime if the index of O is smaller than the index of O prime. So, this, and later on we'll see, in fact, you can check that if you choose S to be any particular number, the number of operators that could possibly have that index is finite. And again, this is useful because it encompasses several interesting cases, and what we'll see later on when we look at the renormalization group of effective theories, it's really useful in organizing the possible renormalization group contributions to the evolution of various couplings. So here's my index. Oops, at the top here. It was just a reminder of what it was. And let me consider now 3 special cases that are, as I said, of use, of interest. One of them is when you choose this arbitrary real number to be 4. Then the index becomes this thing, which is exactly the dimension of the operator -4. And so when I say that I'm classifying operators according to their index, I'm really classifying them according to their dimension. And what I told you is that lower dimension operators are more leading or can have stronger effects than higher dimension operators. And that is true, because higher dimension operators come with a larger number of lambdas in the denominator, and so their effects are correspondingly smaller. Then there are other cases I want to consider. One of them is when u is equal to 1. In that case, the index just becomes the number of derivatives minus 1. Just period. That's it. So it's kind of a derivative expansion. And this is interesting for a theoretical model that, as far as I know, has no useful phenomenological application, just strongly coupled supersymmetric theories. I'll give you an example tomorrow. And the last one is choosing this u equal to 2. In that case, the index becomes the number of derivatives plus half the number of fermions, minus 3. In this case, then this is an ordering of operators according to the number of derivatives and the number of fermions they possess. This is useful for low energy QCD because in low energy QCD, pions are very easy to get. Pions come for free. And so having an ordering that doesn't depend on the bosons, which are pions, is very useful. And in fact, this object here is S. This is what is used for ordering operators in low energy QCD. Low energy QCD is not a decoupling situation. This is a theory that is strongly coupled, QCD, and you're just observing it at low energies. It is interesting, and you can ask, at low energies, what do I see? Well, again, it's the same prescription. What do you see at low energies? Pions. You're done, get pions. What are the symmetries? It's a chiral symmetry, SU2 cross SU2, and then you're done. You have the pion fields, you have the symmetries, you construct all the operators that have pion fields that obey the symmetries, and you add them all up, and you get the whole description of pion interactions at low energies. And that's low energy QCD. And the ordering, and again, there's an infinite number of operators, but they can be ordered. And the ordering is obtained by this quantity. You might ask what the fermions are. Well, low energy QCD also has baryons. They're heavy, but they're there. You can consider them. And so now you have a theory that has baryons and pions. And you ask, how can we write down all possible baryon-pion interactions at low energies? And this is a theory that does that.
Is there any special reason for these choices giving rise to these examples? Or?
You know, so the question is, how the hell did this come about? Okay, it's said much more politely. And the answer is, I really don't know. I'm just telling you that there is this expression here that looks very bizarre, that if you choose u equal to 4, it allows you to order things as we do for a decoupling theory. If you choose u equal to 1, it allows you to choose an index for ordering operators as we do in strongly coupled SUSY. And if you choose u equal to 2, it unifies these things. I don't think there's any profound anything at all in it. It's just useful, kind of thing that not unifies. It encompasses all three cases. There's no physics in this. It's just a good record-keeping way. That's it. There's no physics. Don't read more than that into it. So let me stop at this moment. At this time, tomorrow morning, I will go through each of these cases in a little bit more detail, and see how they come about and how the ordering is achieved and why this ordering is of use in each of those situations. Thank you. So, yeah, I didn't ask for questions because tomorrow I'm going to give you time to do the questions. So think about it a little bit, and then you can ask as much as you want tomorrow, okay? Because we all want to have tea. Okay.
No, there are some questions.
There are some questions right now. Oh, I'm not going to stop. Please, ask questions. I intimidated them. I'm sorry. Don't be intimidated. Ask questions. Or wait until tomorrow. That's also okay.
Okay, so then let's break for tea.
Let's break for tea.
Yeah.
And reconvene for the seminar. Thank you. It doesn't turn on.
and how?
So am I audible from back? Okay. Good. Okay. So thank you, Subhaditya, for organizing such a school for these grad students, and thank you, Jose, for coming down from this long distance to teach us about this thing. So my role in this one lecture is very much supporting. So what I will try to do instead of going into, yeah, should I come this side? Okay, great. Am I visible now? Okay. Okay, this is more fine tuning than the effective field theory, I guess. Yeah. So okay, so what I will plan to give you a sense of what is effective field theory, which already Jose has introduced to you, and then how you should use that. So rather than going into detail in one of the specific construction, I will try to give you a glimpse of those ideas and try to motivate you that why this is the right time to do the effective field theory. So let's see. So the interesting part of physics is basically, as you know, the physics of different length scales are actually different. So if you have heard about the word like the theory of everything, that doesn't make any sense in real scientific community, because at different length scales you have a different kind of physics phenomena. So now if you look into very natural unit point of view, so you can connect this energy, mass, and this length and time. So everything we can recast in terms of the energy, and that's what the one scale when I'm talking about repeatedly. I will not mention the mass scale or whatever, but uniformly that I will be using the mass scale for that. And now if you look at the experimental searches and versus the theoretical proposals, so that actually encompasses the directionality of the scales. For example, when you construct a theory model builder, right? So what you try to do, you try to use the symmetry and all those information about the quantum fields and so on. You try to write a Lagrangian on that thing, and you try to predict something which you expect to be discovered in the future. That means basically in the much more higher energy scale. And experiment actually try to dig out those energy scales. So it's like a complementary behavior from their side. And if you look into already our known range of scales, so if you see around the mass scale of muon and the I guess this electron, and that's basically the low energy theory we talk about. And there one of the interesting phenomena is basically that actually opens up the notion of the effective field theory is the fourth Fermi theorem muon decay, and I will come back to this example. And then if you go a little bit more higher energy side, then you find out the standard model where you have a different kind of hierarchical masses. So you're starting from top mass to W mass, and all those scales are there. And this much information we have already explored in our experiments, but we have different kind of ideas that this can be the complete way of looking the nature looks into this low energy or different kind small length scale physics. So maybe something more is waiting for us, and that's what we call the beyond standard model. And actually, unfortunately, so far we do not have any definite clue about the beyond standard model. So the idea or the game is to basically boils down to the fact to understand or maybe find out a good mechanism to understand or pin down what is the beyond standard model. It's a model building way of doing that, or effective field theory can play a very important role to do that thing. So you can see that I was talking about the theoretical proposals, and the phenomenological explorations are actually giving you the complementary notion. For example, you start with a low energy theory, right? And then based on the symmetries and the quantum fields and informations, what you do in a bottom-up approach. So when in the bottom-up approach, basically from the low energy theory information you use, and you try to construct a theory at the high energy. And here you are actually have no clue what could be the unique theory. So better you rely on what are the informations that you have, and you use that to predict kind of a high energy theory. This is a bottom-up approach. And another way to look into that, okay, so you start with your favorite theory, which you define as a UV theory or some high energy theory, and then you know what is not part of the standard model on that UV theory. Okay, and then if that mass scales, as Jose was talking about, the decoupling and all those things, then the decoupling limit, certainly away from the electric scale, then you can integrate that out, and then you basically construct a low energy theory there. But these two are actually complementary, and they are connected by an interesting bridge, which I am calling unfolding. What is that? For example, it can be the other way around also. For example, from the experimental point of view, experiments doing different kind of fittings of effective operators and so on, all those things, and then you basically know, okay, along these effective operators there are some X's on those things. Now the next question would be, because that is our primary hunch for that, what is the theory that can explain that data? So instead of having a blind hunch, what we can do actually, we can have a symmetry driven way, we can unfold those effective operators and try to see what are the minimal way to extend the standard model to such that we can explain that data. So these are the three important things which actually develop in I would say modern aspect in the last 10-15 years. So now coming back to the again slightly repetitions what was already told, what is the effective field theory. So this is like a technique, of course, it's like a quantum field theory technique that smells the presence of some unknown physics if it is there in the corner without much knowing or unfolding about that aspect, right? And we have already seen there are two distinct and complementary approaches, which is like a bottom up from the low energy theory to high energy theory, guessing about that thing. And if you start with some important or interesting phenomenologically relevant some UV models, you just integrate that out and then come back at the low energy in terms of effective theory. So these are two complementary approaches. Now bottom up approach is basically introduced in a much more primary way of the effective field theory, because that is actually the essence, it contains actual essence of the effective field theory, because that is what it was built for, that if you do not have any clue about the UV theory, but I have a low energy theory and the information, what I can say maximum about the UV theory. But then there is a complementary behavior top down. So though it is called the effective approach, but if you think carefully, this is actually the effective way of doing the full theory calculations. Okay, so you can do the full UV theory calculations, okay, and then you can have your predictions of all those things, but we can do integrate out if the UV scale is away from the low energy scale, and then we can reduce the UV Lagrangian into an effective Lagrangian. So it's like an effective way of doing understanding, and why that will be useful, it will be clear when I talk about those things more. And we will learn to blend these two methods to suitably solve our big question. Okay. And these are some useful references for effective field theory. Okay. So now this is the big question. So we have predicted actually 1,000 and thousands of UV models. Okay. So every day we come up in archive some new models. Either we change the interactions, we change the quantum number of the fields, and we write a new Lagrangian. Okay. So in last since the promise of the LSC, we have built possibly more than 50,000 models. Now the question is really, what does the nature going to follow? Okay. So then even if we find out some kind of excess, okay, the next question would be, how do we discriminate among those 50,000 models? Okay. So that's why the kind of question that we want to understand, that there is an inverse problem. If you have some kind of excess, okay, now what is the best way we can translate, if not pinpointing the exact theory, but what kind of mu physics can encompass that excess? Can you talk about something, and can you use effective field operators? Okay. And then what you do, you start with different kind of UV theories, and these are, let's say, this capital phi are basically non-standard model particles, and these are heavy because our search in the LSC actually signifying that the new physics scale is basically away from the electric scale. Okay, so that's enough motivation for us to say that these particles are possibly far away from the electric scale, and we will integrate them out. And once we integrate them out, so whole this UV theory actually land up here. So the interesting part is basically the big pond that you have constructed, whatever be your UV theory, as long as it actually after integrating out, if it respects the symmetry of the standard model and it contains only the standard model degrees of freedom of the particles, the number of operators of any dimension cannot exceed this one. Okay. This can be proved actually field theoretically and mathematically. Okay. So then you basically get these islands, right? So now you take a different theory. Okay, you do the same job, you just leave standard model degrees of freedom untouched, such that at the low energy all the operators are basically constructed out of the standard model symmetry and the standard model fields. Okay. So now you do the same job and you get a different island. Okay. And now what you see, you continue doing that thing, and what you will find out, okay, you start with the minimal extensions of the standard model. You extend the standard model by minimally by, let's say, one particle, either as a scalar of different quantum numbers, or as a fermion of a different quantum number, or a heavy gauge boson of different quantum number. Okay. But once you integrate those non-standard model degrees of freedom, okay, all the theories to start with were like apple and oranges. You cannot compare them, right? Because let's say standard model by a heavy scalar, the 2HDM, 2 Higgs model, okay, or you have a standard model extended by a vector like fermion. I mean, there is no way you can compare them, okay, because the parameter spaces are different, their interactions are different, but this thing allowing you to now give a platform where you can really compare them, because you have reduced both the theories on a platform where it described by the same degrees of freedom, by the same symmetry, right. So now this apple and orange are reduced into some effective apples in both the contests. Now you can compare them. So that's the better handle to that thing. So, but on top of that, there's another one is basically tracing back the UV scenarios. So it may happen that from the experimental point of view, even knowing any particular theory, you may come up with some, let's say there's a effective operators O1 and O2. And now you get some excess. For example, a few years back, there's some excess in the atlas about the CP violations. Okay, exactly dimension 6 level. These operators actually can explain the CP violations. So you have O1, O2, and O3. Okay, and now what you do, we are saying that in a symmetry-driven way, you unfold the operator and to find out how minimally you can extend the standard model such that once you integrate out those heavy modes, you get the O1, O2, O3. So this is instead of having a blind hunch, that's a symmetry-driven way to understand that there is the excess in the effective operators, and that can be explained by these minimal extensions of the theory, but at least 1, 2, 3 theories. Okay, so you can make such a list of such kind of theories based on this technique. Okay, so now these 3 pillars that I talked about, that can be nicely understood in terms of very simple, which you know as the 4 Fermi theory. Let's try to revisit that part. For example, if you introduce the muon decay to the 4 Fermi operator, and the constant basically GF, which is of course lambda to the minus 2 as the mass dimension, and then once you introduce this thing, then Jose already mentioned about the unitarity and the violation of the unitarity. So you can see the cross section actually increases with the energy, and that's a clear violation of the unitarity actually. Okay, so that's what it means basically, that the energy scale where you are computing, that's actually interfering with some kind of new physics. Okay, so it's not about the fault of the theory. This theory is actually effective theory. So this has some kind of limits. Okay, you can't use effective field theory arbitrarily for the large energy scale. But what you have introduced the effective theory, but you do not know where exactly effective field theory should be stopped. So whenever there is a failure of the effective field theory description, that's also, I would say, a good hint for the new physics actually. So that's what we come up with the idea of the intermediate vector boson and so on. So that's another bottom up approach, because you have these degrees of freedom. Okay, you construct a 4 Fermi operator, which is this one, and that's the bottom up construction, because you have low energy theory, you have symmetry, and you construct this 4 Fermi operator, right. And now if you look at from the standard model point of view, now you can perform the same process using an intermediate heavy vector boson, which is the W, right. It's a massive one. You have the propagator, you expand the propagator, which already Jose has mentioned, and now, and that's what, when I'm performing the expansion of the propagator, it's actually nothing but the integrating out. It's the actual T level integrating out. So whatever you are doing actually, you have a propagator in the denominator, which is actually non-local term, and now when you're expanding this propagator with a momentum transfer through the propagator is much less than the mass of the propagator, actually you are writing all these non-local terms, the infinite sum of the local operators. Okay, and you are truncating, believing that the momentum transfer is such that up to some k square by mw square to the power n, for n is 5, 10, or depending on the value of the k, you are truncating. Your truncation is allowed. Okay, and that's what the integrating out. So now we have understood the same phenomena, and we are getting the same operator here. But now we can see that we understand the same bottom up approach and top down. And the other way, even if you do not know the standard model, for example, if you start with this thing, now what is the unfolding tells you? You basically know the quantum number of these states. Okay, now you basically try to find out, okay, what is the minimal extension of the gauge boson, what is the gauge quantum number you have. Then you find out, if you use the SU3 cross E1 quantum number of these fermions, then automatically you will find out the spin 1 object and what is the quantum number, how it should transform to the SU2 adjoint and so on. So you basically know that if there has to be some gauge boson, okay, there has to be a massive spin 1 object. Okay, and that's what the the unfolding implies. Those 3 topics that I mentioned is actually is well understood through this simple 4 effective fermion theory. Okay, so now effective field theory is a very old tool, but the way we are now trying to understand the effective field theory, and we try to use and making it very relevant and try to construct something, it's like a going on a war. So you better have a good weapons in your arsenal, and that's what you call the EFT arsenal. Okay, So these are the three things you must have if you want to make some good contribution in the effective field theory, and you use that. So these are the theoretical advancement in the effective field theory. Second is that use them because you have to classify more and more UV models. So you need better define an algorithm, and you develop your own open source programs and use them, and in collaboration with the experimentalist you perform the fitting and all those things. So these are three pillars of the modern effective field theory. And these are some useful references in those directions. So I am just skipping them because there are some open source programs also there we have developed recently, but I am not going to talk about them in detail. Okay. So now let's focus on the bottom up approach because it's the important one, and it actually contains the basic essence of the effective field theory. So here when I am talking about the construction of the Lagrangian, the invariant, so I will name it as like invariant polynomial, because that's what it does actually, right? Because you have some symmetry and the you have the quantum fields, and when you write Lagrangian, what you write down? You write down operators which actually are invariant under the symmetry. And as Jose also mentioned, that if you have more than one symmetry, that operator must be singlet or invariant under individual symmetry. That one has to be careful. But game is slightly more complicated than that. So these are the rules of the game. You treat the quantum fields are basically nothing but the equivalence of the particles, okay, the symmetry, and you basically look for the representation theory of the quantum fields, and the quantum numbers are nothing but from the outcome of the what is the representations of the fields. And in my language, the Lagrangian is nothing but a collection of the singlet or invariant operators, okay. And as I mentioned, singlet are basically which does not transform under the symmetry. And what are the symmetries we should be careful about? Compact internal symmetries, for example, starting from U1, SU2, SU3, okay, it can be some kind of spin groups, spin 4 or spin 6 and so on. It is sometimes you can gauge them, sometimes there is some global symmetry. For example, in the concept of standard model, you have the baryon number, lepton number, E1 symmetries which are basically accidental, but they are the global symmetries, okay. But you have also the gauge, hypercharge, weak symmetries and the color symmetries, but also you have a global non-compact symmetries because you have a space time, right, and that's how you define the spin. Without them you cannot define the spins there. So you have a non-compact global symmetries, and fortunately the kind of theories we are talking about, we don't need to gauge them because we are exploring the supergravity and all those things here, okay. So there is symmetry information we have. And now while doing that, we have to, the idea is to construct the higher mass dimensional operators. Now when you do that, you basically you can construct as many operators as you want to, but there is some restriction because the construction has to be like they're independent operators. Now when I am saying independent, what do you mean by the independent? So these operators individual, they are like a fields, they have some equation of motions, okay. So now once you construct multiple operators, let's say at some dimension 6, okay, you write down 1000 operators, okay, but not all of them are independent because you have the equation of motion up to dimension 4 Lagrangian for fermion, for scalar field, for gauge field, right. And then once you use those equation of motion, then you will find out that these two operators O1, O2 are basically exactly same, or they are differ by a total derivative, okay. So if they are exactly same, then you can understand that the equation of motion connecting two operators. So if two operators or multiple operators are connected by the equation of motion, I will call them redundant. So if there are 5 operators which are connected each other by the equation of motion, I will pick one of them, and that is the primary goal, to connect not only constant operators but non-redundant operators, because in Lagrangian you cannot write down same operator again and again in a different form, okay. Now why I am stressing on the total derivative? Because the quantum field that we are actually constructing here, okay, there is no boundary, right, and if there is no boundary, there is no boundary conditions. If there is no boundary conditions, we are not worrying actually about the boundary operators. So now if there is no boundary operators, so the topological terms and boundary operators we are actually relevant for this construction as of now. So if two operators related to each other by the total derivative, we just say we will declare them to be same, okay. Now what are the integration by parts? Remember the Lagrangian density content is the polynomial of the operator are actually there, right, but actually the game is basically with the action, and action is basically d4x. If you are working in a 3+1 dimension, it's a d4x Lagrangian density. So then there is a possibility you can use, because of the presence of derivatives, use the integration by parts and so on. Now if you do the integration by parts, then two differently looking operators may be brought into similar form up to total derivative, or not even sometimes total derivative is not needed. Okay. That means basically these two operators are actually same. So when you construct the operators, you construct the operators order by order in a mass dimension. Okay. And then for example, let's say dimension 6 I am talking about, at dimension 6 what are the operators there, then I have to filter them out, saying that they are not related anymore by the integration by parts and the equation of motion, and then we will find out, okay, if I rely on the baryon number left number conservation, if I subtract the flavor, all those things, then I will get 59 operators. Okay. And these 59 operators I can mathematically ensure that they are there irrespective of whatever be your UV theory. When you integrate them out, what are the operators you can generate, you cannot get beyond this 59. And that was the, if you remember that cartoon, there is a big pond I was talking about, that big pond is nothing but the 59 operators. Okay. And once you extend higher dimension, for example dimension 8 and so on, okay, so then of course you encompass more and more, but the game is basically the same. Yeah, any question? Okay. So let me give you some example of that. For example, when you talk about the fields now, as Jose also mentioned briefly, so let me revisit that part. What about the gauge fields? Because when you construct the operators, okay, we have to be also remember the construction is a gauge invariant way, because if you spoil the gauge invariant, then you are really in deep trouble. So if in the operators the gauge fields do not appear on face, okay, they are actually hidden within the covariant derivative or in the field tensor. Okay. And then among these only scalar, fermion, covariant derivative and the x mu, they are actually appearing in the operator. And in this construction, though this phi, psi and the x mu, they are actually treated as the quantum fields, but also will upgrade the status of the covariant derivative as a Spurian quantum field. Okay. Because it is singlet, it does not transform the internal symmetry, but you have to remember they transform under the space time symmetry, okay, as a bispinner. If you think about the SU2L cross SU2R, okay, they transform as a bispinner. Okay. And then the operator, the composite operator that you are going to construct, they are actually polynomial of these 4 fields, and then the mass dimension of the operator is related by this one. Okay. And it is better to construct this operator in the while basis, because that is how decouple your SU2L and SU2R part, and because while constructing all these fields are treated to be massless, so there is no issue with that thing. So now if I, for example, if I have this, these are the quantum numbers under this space time symmetry, and these are the quantum numbers under this standard model gauge symmetry, then we have to go step by step. For example, we will ask the question, what are the polynomials or invariant terms which are basically in a singlet under the space time symmetry. Okay. So those are basically called the scalar. Okay. So we have found out 5 to the power 5 is a scalar. Okay. Fine. But again, when I declare this as a part of my Lagrangian, then I have to make sure that all these operators, all these terms are invariant under the individual symmetries. So but if you look at the quantum number of this phi, then 5 to the power 5 is not E1 invariant. Okay. And also it may not be invariant of other quantum numbers. So though it is a Lorentz scalar, it is a singlet under or invariant under the space time symmetry, but not under the gauge symmetry we are introducing. So this is not a gauge invariant operator. So I am not allowed to write that operator in my Lagrangian. Okay. So that's why I construct the operator, and you have to check that they are invariant under the individual space time symmetry and the gauge symmetry, and if you have some global symmetry and so on. So yeah, so this is the like a standard model, all the quantum numbers are there. Sorry. Oh, I think while making a PDF something is missing.
No, this is a fraction of, this is how do you open the PDF is a question. Opening is an expert of this.
How do you open the PDF?
No, there is one for one, I mean if it is open with Acrobat Reader, it doesn't show the steps. There is one special way of what you can use it to open. This
Okay, let them fix. In the meantime, if you have a question. Yes. 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 So I will come back to this thing when I talk about the defined models and then overlapping thing. I will discuss that thing. Yeah, definitely. Okay, if it's not there, leave it.
No, it's okay. I mean, Hold on for a second.
Okay.
It will come. Slide change করে রাখতে পারেন। হ্যাঁ, হচ্ছে।
Yes, yes, you know, sir.
Now.
Oh,
I mean, we learn from our mistakes.
yeah. So this is not a change of basis then, because it signifies effectively observables. Okay. So yeah. So now, if you look into this standard model symmetries here, okay. Now the spin, mass, dimensions, and the quantum numbers are there. Now you see in the Lagrangian, and the method I am talking about to construct the effective operators. Let me remind you, this is not only for higher mass dimension. Starting from any mass dimension operator, even the renormalizable operators you can construct in the same way. For example, in the Wudka sector, you can introduce this operator, right? It has a mass dimension 4, and look at the SU3, SU2, E1 quantum number. So SU3, SU2 they are singlet, and E1 is total is 0. So of course this is allowed term because this is a chiral term. And now if you talk about the 4 fermions and look at this mass dimension 6 and look at their SU3 quantum number and E1 quantum number. So this is an allowed term. Okay. So this is actually you generalize this thing. Okay. But certainly one can understand that okay. So it's a it will be naive to say that by hand you can do all these things because there are more complicated structures. Okay. And so it's a bit difficult, and so what we did actually, we introduced this for you guys. So there's a program called group invariant polynomial. So where you inform this program about the symmetries, okay, different kind of quantum numbers, okay, and you just tell them, and then it will give you the invariant polynomials. And not only for standard model, you extend the standard model by some any arbitrary particles, but only restriction is basically this works for space-time dimension 3+1, and I think that is enough for the time being for the being a particle physicist. Okay. Okay. Yeah. So yeah. So now, so this is another way to look into the bottom-up approach. So as I mentioned, there is a standard model Lagrangian. You look into this process, okay, and then you believe that this process is not sufficient, to explain all the data for this scattering. So what you do actually, you extend by adding these effective operators. Okay. You are not changing the symmetry, you are not changing the on-cell degrees of freedom, you are just adding them higher and higher mass dimension operator. And once you add them, then automatically along with this diagram, there is an additional diagram pops out here. And now this both the contributions should match with the experimental evidences what you have seen, and that will eventually constant this parameter. Now in this construction, while throwing this one, this lambda and the c, they are the unknown, right? So that's why the Wilson coefficient, the coefficients sitting in front of this operator are called the Wilson coefficients, and they are basically I do not have any clue about the origin. I am just throwing like a free parameter the way we introduce the Yukawa couplings in the standard model. Okay, we do not know what is exactly origin of that, what is the value of that. By fitting we can perform, we get to know about them. So similarly, you just throw them here. So that's what the summary of the bottom-up approach, and that's what you do with the bottom-up approach, and that far you can go. And these are the example of SMEP dimension 6 operators, and I was talking about the 59 operators, and I think it will be revisited by Jose again later, so I will not spend much time just to display you what are the interesting structures of this kind of operators. Yeah. So now, like in quantum mechanics, as you know, that you can change your basis, because basis is not a fundamental thing, right? You can change your basis keeping your observable same. So the same game you can play here. For a given mass dimension, okay, you don't need to restrict yourself to particular basis of operators, because you have a power of IBP and equation of motion. You can go from one basis to another basis, and the choice of basis is sometimes driven mostly by the phenomenological reasons, because in some all the informations are hidden everywhere, but sometimes some of the informations are very explicit in some of the choice of basis. Okay, and that's why we generally choose depending on what kind of phenomenology you want to do different kind of basis. For example, one of the famous basis by the Warsaw group is the Warsaw one, and then the strongly interacting light Higgs is the SLH basis, and you can see that how they are related to each other by this nice equation of motion and so on. So you can go from one basis to another basis depending on your choice. Those kind of freedoms are there. Okay, but before proceeding, you have any question on the bottom approach? No. Okay, so now let's talk about the other one, which is the top down approach, which is effectively integrating out the heavy fields. Okay, now when you basically integrate out, what you do basically, you have a low energy theory, what I have already mentioned. Okay, you start a UV theory, and you at some scale you match them, And generally the first scale that we talk about is the mass of the lightest heavy particle that you are integrating out. So that is the mass of the lightest heavy particle is basically the scale where you are performing the matching. Okay? And then once you perform the matching, then it's not guaranteed that all the operators of the effective Lagrangian will contain only independent operators. Okay? Then you have to pass through them equation of motion, integration by parts and so on, such that you can map that effective Lagrangian into a non-redundant basis of operators. Yes. Field definition is the equivalent statement for the equation of motion up to dimension 6. Beyond dimension 6, there are something issues are there, but one can still tackle it by modifying the quantum equation of motion. Yeah. Yeah. Any other question? Okay. So one has to keep in mind that these two constraint is not only true for the bottom up, but the top down also you have to keep in loop about those aspects here. Now, what is the funny story about the top down is that you start with the now UV theory, okay? And let's say you are looking at this process for a UV process, okay? And then there is some pure standard model process like this, and then pure new physics process which is involving only new physics particles. At a low energy, this is redundant for us. We are not interested. We are looking for the only on-cell state which are actually standard model particles. Now, when I am integrating them out, that means I am expanding the propagator in terms of local operators, then I am getting this. Now, if you recall what I do this diagram for the bottom up approach, you start with the standard model and then you add this operator. But here you are generating this operator, and because you are generating this operator, there is some advantage of doing that, because now you know what is the source of the operator. So you know exactly what kind of UV theory can spits this kind of operator. And not only that, these Wilson coefficients will be function of the mass of the heavy propagator and the couplings. So they have now the origin, okay? And this is basically a huge difference between the bottom up and the top down approach, because in the bottom up approach, if you add 10 operators, those 10 operators are originless, they are free parameter. So when you perform the fitting of some observers, as you know, you have to treat them as a free parameter. But if you are coming from the UV theory and you generate exactly the same 10 operators, but though they are now exactly the same 10 operators, but they are actually function of 2 or 3 BSM parameters. So effectively the degree of freedom is reduced. This kind of theoretical correlation among the effective operators and the Wilson coefficient, that is actually there for the top down approach, but the bottom up approach, that information is missed out. So that's why it is not suggestive to use or translate directly the bottom up approach result for the top down. They can be completely misleading. Okay, because yes.
The same operator can come from different UV theories.
Yes.
Then how one can distinguish which UV theory?
Yes, so I will come to that. Yeah.
So bottom approach classifies this cannot, unless we consider all operators or possible dimensions.
No.
It cannot retract back any specific model, right?
No, so it depends on what kind of it guided by choice of your observers. So once I fix my observers, I know exactly what set of operators I have to deal with. Because other operators are, I will call flat directions. They are not sensitive to my observers. Like in BSM, for example, UV analysis, when you do, you can have 10 parameters, but not all of them are sensitive to my data.
Isn't it they classify specific class of models, so these operators can come from this class of models? And
No, so that's the classifications. That's the classification. I'll talk about later that thing. Yes. Yes. Any other question?
So in the top-down approach,
Yeah.
so when you have only the relevant operators which are suitable to the UV theory,
Yes.
so at that time, is that meaning that you are missing something like some other effects which are not within the model?
What do you mean by that?
Like the effects, the model is not.
No, you declare that as a UV theory. You believe that's the complete theory of nature, okay? Or what you can do if you don't believe that, what you do, your UV theory, if it is an effective theory, let's say, then you add more higher operators on them.
I think he is asking the most difficult question. He is saying that whether effective theory can completely, whether it can completely replace your full new physics or UV complete.
No.
So
UV effective field theory, that's what's effective. Yeah. It's better to deal with. First you have to understand whether there is a new physics around or not, because once you understand, then presence of the new physics, then you have to do the full theory analysis. Yes.
So, I mean, it was that kind of a question, because say for example, I mean the dimension 5 operator, if you take, I mean there are many new physics models that it can correspond.
Yeah.
But so therefore the effect of the dimension 5 operator cannot distinguish the possibilities of these three different patterns.
No, that's not possible. Yeah.
That's not.
Yeah. I mean, that's not the in fact purpose of the effective field theory at all.
Yeah, because
Yeah.
now we don't know.
Yeah.
The point is whether we can see.
Okay. So I'll take 2 minutes because you talk. Okay. Any other question? Okay.
I'm going to shut you up.
Okay. Okay. So now, what are the diagrammatic or pictorial way to look into this integrating out? So this tree level I have already mentioned. Okay. And so now you can have a one loop diagrams. So in the one loop you can have a different kind of topology. For example, you have a propagators which are actually only new physics. So all are basically heavy propagators. Okay. So you can shrink them to a single point, or you can have a this kind of diagrams which also contribute to the effective operators. Okay. For example, you can shrink these two propagators, but certainly you cannot shrink the standard model. And these are very non-trivial diagrams because these actually contribute to both local and non-local contributions. But what we are interested in the local operators, so you have to really remove the non-local contributions. Okay. But I will not go much detail about all these things. Okay. And this is one of the program that we developed, that if you plug in basically some UV Lagrangian, okay, and then you start to integrate that out, okay, and then what you can generate basically the one loop effective action for tree level process. Up to one loop you can integrate out this using this program, and not only that, after generating those effective Lagrangian, you can just run them down to the electric scale. Okay. So that's what you can do with this thing, and this is the website where you can go much more detail about this. Okay, done. So what did you do?
Press the button once more. Yeah, see that experience works.
No, but it gives me skip some slides.
No, it didn't.
I know my slides. No.
This slide was very fast.
Why don't you come and check here instead of So all this will be part of the injury time, right? You know, in soccer you have an injury time. So yeah. Again, so you have a time to ask some questions, because we are dealing with the irrelevant operators, so it doesn't matter if you ask me irrelevant questions also. Yeah.
So for the unqualified,
Yes.
so let's say we have some observator.
Mm-hmm.
Motivated from that observer, we are like going to the direction of the unit field.
Yes.
So there may be different unit cases.
Yes. Yes. Not only that, you have to do you have to take a policy of that. For example, if you believe on that thing, like I'll do that minimally. That means with the standard model, I will not extend the standard model by too many particles in a single shot. Can you explain by a minimal, interactions or the particles? So yeah, but still you can have multiple solutions for that.
Yeah, that is minima. If we do minimally also, that there may be two theories.
Yes.
Two theories,
Yes.
And those are the as
Yeah.
minimal, you are the compatible.
Yes.
Because of same minimum.
Yeah.
So then,
Yeah.
is there any preferable thing?
No, so generally what you do then, once you identify those two theories, okay, then you integrate that completely now. Then you generate complete set of operators. Okay, so it will not generate only one operator, it will generate more other operators, right? Then you see what are the non-overlapping set of operators and how to discriminate using them. That's the next challenge. So it's like a go and forth kind of analysis you have to do to break those kind of degeneracies. Yeah. Yeah. Okay. Okay. Thank you. But in this mode will it change? Oh, great. Yeah. Okay. So, this is the third one about the unfolding, but I cannot talk you in much detail, but give you the essence of that. So, you start with the observation data, okay, and then you construct the effective operators to, because there are the relations you set up with the observables in terms of the effective operators, right, and then you try to fit them and try to understand what are the effective operators actually are relevant for this kind of analysis, and then you basically unfold to see what kind of UV models you generally have. And that is what you do. You start with basically anomalous behavior of the observables, you identify them, what are the relevant SMAP operators, okay, and then you unfold them in terms of Feynman diagrams, pictorial way, and the background you basically use the knowledge of the symmetry to identify the heavy field propagators, and you can land up with the multiple solutions. For example, if I have, let us say, this kind of operators phi square x x tilde, x is basically nothing but the field tensor, okay, and then you will find out that you need at least two different kind of heavy fermions which are vector like to get this operator if you unfold that, okay, and that will lead to CP conserving and CP violating both sector operators. And then once you use that knowledge, then on the other hand side you use the program that I suggested and you plug in this Lagrangian, and then you will find out exactly this operator you are generating. So, that is the complementary way you can understand, okay. So, how from an effective operator you unfold and get to know what are the minimal way you have to extend the standard model, and then once you extend the standard model, plug in that Lagrangian and generate all the operators and then perform all the fitting and all those things. So, that is the go and forth kind of approach you have to do. Okay, so now I will tell you, so what are the phenomenological way to look into this aspect. I believe Shankho and will talk about, and Subhaditya also will talk about more about those things. So, what we do generally, so different kind of experimental data we use, but more pinpointedly because they are the electric equation data which are very useful because they rightfully measured quantities, and we use the Higgs data. Specifically we use the differential cross section just to get to know about the PT and all those things, their behavior, and then we estimate the deviation from the standard model, and we try to recast some structure in terms of the effective operators, and then you find the depending on what kind of approach you want to do, you define the chi-square or in a Bayesian way, or some modern approach, but effectively it boils down to the fact that how do you constrain them. So, based on this you can now classify different kind of BSM theories. So, how you do that thing? For example, let us say I constructed I thought of like a 15 different scenarios where the standard model is extended by one heavy scalar at a single point of time, and this is a minimal way you can do. So, you choose some different color singlets object, you can see all are basically color singlet, and then you have a colored object which you generally know in the literature as a electroquarks and so on. And then what you do, you choose one model at a time, you integrate out that thing and then try to find out up to one loop, okay, what are the dimension 6 operators you are generating, and that is this. Okay. So, what you find out that if you have these models, and then if the HH tells you that these operators dominantly generated at the one loop, okay, and that also to the heavy propagators only, and then the cross means this operator is not generated up to one loop, okay, beyond one loop we do not know, but up to one loop we are doing this thing. And now you can see the lot of operators are generated by the same set of models. So, that tells you that though we as a model builder claim I have defined a new model, I have constructed a new model and put in archive, how defined is that? From the effective field theory sense of that, they are not much defined. It is like using a defined mask, you are playing the same game. Okay. Okay, so this T stands for this operator dominantly generated at the tree level. Okay. HH, your heavy loops are contributing.
Those are HH.
Yeah. Very bad projector, Yeah. So no, yeah. So now, so this is like an optics lab, possibly most of you have visited. So what you have done, so you have a, let's say you have a fine screen you have invented, which can is sensitive to kind of a single frequency, and if you pass let's say white light, okay, which contains a different kind of frequencies, and then it will spread out the frequencies and it collect on that way. So this is a similar idea. So basically all these screens are nothing but my set of observables. Now what is my observables? Observables are nothing but my set of operators actually. So now what I do, I pass through this 15 models through this. Now depending on which operators they are generated, their sensitivity to this observable will be based on that thing, right. And then what we find out in the first time that okay, so these 2 Higgs double model, complex triplet and complex quadruplet, they are actually equally sensitive to this observable. That means if I rely on only this observable cannot discriminate these 3 different models, or these 3 models are actually on the degenerate spectrum. And similarly all these leptoquark. Okay, so then I extend my new set of data, which is Higgs signal strength, which contains certain more operators, and that then we will find out okay, so these are again affected by the same set of operators and equally good on that. So I cannot break the degeneracy. But interestingly, among these 6, now this S2 contains some operator which is actually sensitive to this one, but which is absent on other 5. Okay, so I am not talking about the realistically possible, I am just from what is the best we can do from a theoretical perspective. So this is the best what we can do theoretically, okay, and that is the break the degeneracy. And then you increase the precision in the electric precision data, use some different kind of observables, and that is how if you carry on the process, and then you can see how the degeneracy in the models can be brought down. So this is the theoretical sketch and what is the best achievable scenario one can have, okay, that if you have a different kind of minimum, and let us see there is a minimal models. Now if you extend your models by multiple scalars, now you can understand they will be more and more degenerate, because they will give you the similar kind of things. So among those 50,000 models, possibly almost 99% models are actually nearly degenerate. Okay. So that is why even if you have some kind of excess, it will be really difficult to pinpoint whose model actually win the race. Okay. So that is what kind of notion we get from the effective field theory. And this is what actually in just one simple plot to highlight the bottom up approach by the versus the top down one. So this is the ellipse which is almost invisible, but I hope you can see this. So this bigger ellipse if you see, so when we have used some H2 and this complex triplet, complex doublet and the quadruplet models, okay, and we integrate them out, we get the 9 operators. Now if I use these 9 operators from a bottom up side, then we are treating them to be independent, right, and if you are treating them independent in this Wilson coefficient plane, we get to know about this is the allowed regime. But once we know that okay, there are some different UV theories are there and we integrate them out, we generate exactly those 9 operators. But now those 9 operators Wilson coefficients are theoretically connected to that, and instead of 9 operators independent, they are function of 3 model parameters, and because they are theoretically connected, so now you can see the allowed regime is basically this minuscule regime. So that is why in a bottom up approach you always get an overestimation, because the number of operators you are adding more, okay, and in the top down way, because they are theoretically connected, so degrees of freedom is much more lesser, it is a much more tighter constant you get. So certainly you cannot use this ellipse information to put bound on the UV theories, you have to perform their fitting in an independent way. Okay, so I am almost done. So there are some fistful of EFTs. So effective field theory connects physics of different length scales, and that we have seen, and it is a very effective tool, especially when the new physics is unknown. And the top down and the bottom up approach, these are two complementary one, and different UV theories can be brought into the same footing, which you call the SMEPT for the time being, and this is a platform where we can perform the comparative analysis between different kind of models to put some kind of bias to understand them better. Okay. And so far we have the real data, we have electric precision data and the Higgs observable, but you never know the theoretical constant, the non-observation from the child electron flare violations and neutrino physics data and all those things. If you put more and more data, maybe that will be more interesting way to look into that thing. And what I didn't talk about much about the, if you have a CP violation, that is very interesting. If you find out some non-standard CP violations, that will certainly be a game changer, because that can help you to discriminate in a primary notion that okay, the standard model is extended by a heavy scalar or a heavy vector like kind of fermion, or there is some kind of axial anomaly also. And the precision calculations are more important, so you have to go either in computing the dimension 6 in the higher loops, or you extend the dimension beyond dimension 6 like dimension 8 and all those things. Computation of the renormalization group equation for the effective operators are very useful, because if the scale is higher, then and the lambda is basically let us say few TeV, and then to the electric scale, that running in the precision era could be very important. So we cannot be ignorant about that thing. And what are the effective field they talk about so far? and what will be discussed, I guess, is mostly in the T equal to 0, 0 temperature, but this is not all about the effective field theory. There are certain huge genre of effective field theory where you have the finite temperature. You switch on the finite temperature, and then that theory becomes more interesting, and it actually widens up the much more applications starting from QCD, low energy QCD, cosmology, and even the condensed matter physics. So I would stop here, and thank you for your attention. Yep.
So let's say we have two UV theories.
Yep.
Hello. Let's say we have two UV theories, and what we want to distinguish between two, and let's say we have observables that lies in, let's say, two energy scale. Let's say one observable is measured in some experiment which is at E1, and another observable is at, let's say, E2. So so to do that, do we need to take the lambda which we take, that thing such that the two experiments are valid for this lambda, or let's say we do for one experiment at a time and then another experiment at another time?
Okay. So let me give an example that way. For example, let's say you extend the standard model by some two heavy particles. Okay, there are two EV theories. Okay, you integrate them out. You basically get the effective operators at their mass scales, and to start with, to make a comparison, you assume their mass scales are basically same. Okay, so that's the lambda, capital lambda. Okay, and then you generate the effective operators there. Okay, you run them down to the electric scale. So electric scale, you have the electric fission data, Higgs data, and all those things. You perform fitting on them. So basically now your Wilson coefficient plane is basically now much more squeezed. Okay, and then what you do, you just started but now you want to use the flavor data, let's say, at the low energy, at the bottom mass. Okay, and then what you do, you start integrating out the Higgs, heavy gauge bosons, top quark from the effective operator and so on. Okay, and then you get a low energy effective field theory at the MB scale. Okay, apart from the running and everything at the MB scale, and then you perform the refit those again. So that is the how one should do actually. Okay, because you cannot merge the scales. Yeah.
Hi. How to determine when to use top-down and bottom-up approach?
Sorry, how to?
How to determine when to use top-down or bottom-up approach?
Okay, so bottom-up approach is basically we give a much more gross idea. For example, you have no clue about the effective operators on all those things. So that's why you perform the bottom-up approach. You basically get a window of the Wilson coefficients. Okay, and then if you are interested in a specific to declassify the models or make a comparative analysis between different kind of UV scenarios, okay, then you do the top down, and then you perform the complementarity among them.
So on the slide there are different models.
Yep.
And there are filters.
This one?
Yes.
Yep.
So what are those colors on the boxes?
Colors in the box. These are? Okay, this is just to tell you that these are singled out from other, because they are not overlapping with other models. So they have their own identity. That means these, once you integrate out this particle, okay, you generate the set of operators, and when you integrate out any of them, okay, you get a set of operators. When you make a comparison, this model will offer you something which is not in others.
Means a set of operators which is not in others.
Yes.
Okay. So can we insert one more filter? So is it done at dimension 6? So can we improve that filter by including higher dimensions, a dimension 8 operator? Which
yeah, of course. That's the precision actually. That's the precision.
Means
for example,
dimension
the
classification.
But you have to, when the observers are also on the same level. Yeah.
Suppose we have multiple heavy fields in the full theory, and the suppose the mass difference between the two new fields is, if it is large, then probably we will first integrate out the heavier particle and then we will go down. And but if they are nearly same masses and two different kinds of new heavy fields, can you tell how do we integrate?
Yeah, so basically your lambda is the light, the lambda is the lightest heavy particle. So if you have M1, M2, M1 greater than M2, okay, M2 is the lambda. lightest heavy particle mass is my lambda, because that's otherwise I can go to energy regime. If I choose m1, okay, I can go to energy regime which is less than m1 but more than m2, right? So then I can create that particle on shell, then my effective field theory will be invalidated. So just to make sure my effective field is validated, I should work in a regime which is far away from the lightest heavy particle mass. So any other mass, heavy particle mass, will be above that. So I am safely do the effective field theory analysis.
So if you are screening things,
Yeah.
so if I rearrange the order of the screen,
Final, yeah, they commute effective. The final result will commute. So it doesn't matter. Because set of operators, right? Linear is.
additional operator means additional observable.
Yeah. So anything you can design by your own.
I have one question.
Yeah.
Is there some prescription given that I want to see some particular phenomena, and given my basis, and I can build up the effective operators which are sensitive to that observables? Like from below side I am taking standard model thing, and I want to see some in the some observables like in flavor violation in top sector. Is there some well established prescription how to make those these effective operators?
So you have to rely on what people have already computed. So people have put a lot of effort to compute the observables in terms of the effective operators. Okay. So if your observable belongs to that set, then you immediately know that this observable will belong, depend on which set of operators. If it is not in that set, then either you or some of your colleagues have to do that job. It's as simple as that. Right? Would you like to add something to that? Okay.
Yeah, you'll give me a job.
Yeah. That's the homework, maybe. Anyway, there's the exam, so homework can work. Yeah.
This is the 9th question. Why we are constructed that SMEFT? Because we know all the degrees of freedom of the standard model.
Yes.
So why we constructed that?
Okay. Because we believe the standard model is not the complete theory. Okay. But we also do not know what kind of new physics could be there. So now using the SMEFT operators, once we include more and more effective operators, because they are supposedly capture the footprints of the UV theory. So to capture the footprints of some unknown physics, we are increasing the higher dimension operators. The higher dimension operators are actually supposed to contain the relic of the UV physics which you do not know. That's why we are constructing the SMEFT.
But SMED operator all are constructed using that standard model degrees of freedom.
Yes.
So there is no new physics or new physics field.
There is no new physics field on shell, but the information of the new physics is there off shell.
Oh, okay. So that is.
Exactly.
That is
for example, let's in the muon decay, if you think about, okay, you integrate out the gauge boson, then you get the 4 Fermi operator.
Right.
But 4 Fermi operator captures the information because your GF actually inversely proportional to the mass square of the gauge boson, right?
Exactly.
So that's why the information is there.
Oh.
Okay.
Any good thing has to come to an end.
Yes. And I am here till 13th. I am leaving on 14th. So till that.
So you are free to bother him with your questions as you come across.
Yeah. Till 6 p.m.
Yeah. So, huh? Yeah, he will buy them coffee. That's Jose's suggestion.
Oh, I thought they will buy me coffee. Okay. Yeah, never mind. Yeah.
Okay.
Sure.
But anyway, it's fascinating to have Joydeep and for his very energetic and enthusiastic lecture to contribute to this Gyan series. So let's thank him once more.
Thank you.
But there is a bit of formalities that we need to do. So we will honor him with a traditional gamusa.
So were you waiting for my talk?
Yeah. So your talk had to be finished.
And they will give you, otherwise we will.
Yeah, exactly. So unless you give a talk, we cannot give it. Yeah. So.
And knowing me for 20 years, he actually can't risk that. Shall I go? Yeah? Or you will come? Yeah. Okay. Wait. There's a video.
Oh, they have the video.
No, but you can skip.
Wait.
Oh.
Right now.
Okay. Thank you. Okay, okay, thank you. Thank you.
So, yeah, we break today and we meet tomorrow, but tomorrow the timing is we start at 10 with Jose. And then we have one lecture and before the lunch and then. Okay, so have a peaceful evening and come back fresh tomorrow. Thank you.